Hello, hello. Am I audible? Hello. लैग करेगा थोड़ी देर बाद आएगा लैग करेगा कुछ भी नहीं सुनते रहना हेलो मेरा तभी है ये भी आ गई ध्यान देना ऑनलाइन बता क्या हुआ क्या क्या नहीं यार ऑन है हेलो हेलो
हेलो हेलो। हाँ, ओपन कहाँ है? हेलो। ज्यादा तेज ना है, हम तो कहते भी तेज तेज बोलते हैं।
ठीक है मतलब थोड़ा दूर से रहेगा ना तो
Hello. Hmm?
What's your name?
Good morning, everyone. A very warm welcome to all present here on this special occasion of the inauguration ceremony of the GIAN Course on Modeling and Management of Inverter-Based Resources Integrated Electric Grid, hosted by Department of Electrical Engineering at MNNIT Allahabad. I am Mahima Srivastav, along with my friend Ayushi Gupta, have privilege to warmly welcome you all to this special occasion. We are truly delighted to have with us an esteemed gathering of scholars, professors, dignitaries, and enthusiastic participants. Let's begin this remarkable morning filled with knowledge, insights, and inspiration. To begin our proceedings, I now humbly request our dignitaries to kindly take their seat on the dais. I would like to invite International Faculty Professor Sukumar Kamalasadan sir, Head of Electrical Engineering Department Professor Richa Negi ma'am, Local GIAN Coordinator Professor GP Sahu sir, Course Coordinators Professor Asheesh Kumar Singh sir, and Dr. Prashant Kumar Tiwari sir. Please join me in welcoming them with a round of applause. Let us now begin this auspicious ceremony with the lighting of the lamp, a tradition that symbolizes the discipline of darkness and the awakening of knowledge. Lighting a lamp is not just a ritual, it is an invocation to the divine, a call for wisdom, clarity, and enlightenment. We invoke the blessing of Ma Saraswati, the goddess of learning, wisdom, music, and art.
सब फोटो खराब कर रहा है
Thank you to all our dignitaries for gracing the lamp lighting ceremony. Now, we proceed to a small gesture of appreciation by presenting a bouquet to our distinguished guest. For this, I would like to request Professor Asheesh Kumar Singh sir to present a bouquet to our today's expert faculty, Professor Sukumar Kamalasadan sir. Thank you, sir. Again, I request Professor Asheesh Kumar Singh sir to present a bouquet to our head of the department, Professor Richa Negi ma'am. Thank you, sir. Next, I request Dr. Prashant Kumar Tiwari sir for welcoming our local GIAN Course coordinator, Professor GP Sahu sir. Thank you, sir. Next, I request Dr. Vishal Gaur sir to present a bouquet to our course coordinator, Dr. Prashant Kumar Tiwari sir. Thank you, sir. Next, I request Dr. Prashant Kumar Tiwari sir for welcoming our course coordinator, Professor Ashish Kumar Singh sir. I now request our GIAN Course coordinator, Professor Ashish Kumar Singh sir, to kindly deliver the welcome address and share his opening thoughts for this academic gathering. Sir, please.
Good morning to all of you. It is my pleasure to warmly welcome you to the GIAN course on modeling and management of inverter-based resource integrated electric grid, organized by the Department of Electrical Engineering, MNNIT, Allahabad. I'm thankful that all of you are here. I can see our senior professors are here, our colleagues from the other departments, they are also present here. We are proud to host this course under the global initiative of Academic Networks, GIAN and STEAM program of Ministry of Education, Government of India, that fosters collaboration between Indian institutions and global experts. A special and heartfelt welcome to Professor Sukumar, our distinguished international faculty member from the Department of Electrical and Computer Engineering, the University of North Carolina at Charlotte, USA. We are privileged to learn from his deep expertise in inverter-based power systems, a domain of increasing global significance. As most of us are electrical engineers here, we know that the 3Ds of power system transformation, decarbonization, decentralization, and digitalization are reshaping the grid landscape with inverter-based resources such as solar PV, wind, and energy storage playing a key role. This shift involves integrating more renewable energy resources, distribution energy resources, generation closer to the point of consumption. and utilizing digital technologies for enhanced grid management and improved efficiency. Inverter-based resources, or IBRs, they play a central role in this transformation. They convert DC into produced by solar panels or stored in batteries into AC electricity, and vice versa, that the grid can use. The growth of IBRs is driving the need for more sophisticated grid management and control systems to ensure stability and reliability of the grid. Alongside the opportunities, they bring new modeling and operational challenges. This course is designed to address those challenges through a blend of theoretical knowledge, simulation tools, and advanced management strategies. We extend a very warm welcome to all participants. It is a pleasure to have you join us from diverse academic and industry backgrounds. We sincerely hope that this platform fosters meaningful dialogue, fruitful knowledge exchange, and lasting academic collaborations. We are confident that the sessions led by our distinguished experts will offer valuable learning and practical insights into the evolving landscape of IBR-based or IBR integrated electric grids. I also take this opportunity to welcome our Director, Professor R.S. Verma in absentia, Head of the Department, Professor Richa Negi, and Institute GIAN Coordinator, Professor G.P. Sahu, sincerely thanking from their constant support and encouragement in organizing this course. I welcome our esteemed faculty colleagues, our senior colleagues, and all the colleagues of the department and outside the department of the institute, and laboratory staff present here. My heartfelt thanks to all of them present here, as well as to those who supported the course in various capacities behind the scene so that we are attending this inaugural session. I welcome the media representatives and the members of Institute media team present here and acknowledge their support in ensuring adequate coverage and documentation of this event. I also extend my sincere, heartfelt appreciation to the Institute administrative staff, the civil and electrical maintenance teams, and the horticulture team for their diligent efforts and unwavering support in ensuring the smooth and successful starting of the course. Most importantly, I would like to extend my deepest appreciation for the support offered by our dedicated student volunteers who have made their tireless contributions. I am especially thankful to my colleague Dr. Prashant Kumar Tiwari, who is the lead coordinator for this course. I am the second man. And for his tireless efforts in coordinating every on-site detail and ensuring that the entire course starts and proceeds seamlessly. Our gratitude is also due to the GIAN platform, who have given this an opportunity for organizing this course and enabling this academic international collaboration possible. I wish you all a productive and enriching learning experience for next 5 days with our international expert. Welcome once again to the Department of Electrical Engineering, MNNIT Allahabad, Prayagraj, and to this GIAN course. Thank you. Jai Hind.
Thank you, sir, for your warm welcome. Next, I invite GIAN Course Coordinator Dr. Prashant Kumar Tiwari, sir, to provide us an introduction to the GIAN Course and its objectives. Sir, please.
A very good morning and warm welcome to one and all present over here. Professor Sukumar Kamalasadan, International Faculty for this GIAN course. Professor Richa Negi, Head of the Department Electrical Engineering. Professor G.P. Sahu, Local GIAN Coordinator, MNNIT Allahabad. Professor Asheesh Kumar Singh, GIAN Coordinator, EED, MNNIT Allahabad. All the faculty colleagues, participants, non-teaching staff, GIAN webcast team, non-teaching staff, ladies and gentlemen. Myself, Dr. Prashant Kumar Tiwari, course coordinator of this GIAN course, and it's my privilege to present a brief report on this particular course. The Department of Electrical Engineering at MNNIT is organizing this 1-week GIAN course titled Modeling and Management of Inverter-Based Resources Integrated Electric Grid under the prestigious global initiative of Academic Network scheme of the Ministry of Education, Government of India, which is currently being coordinated by the IIT Hyderabad. The course aims to provide an in-depth understanding of the theoretical, modeling and practical aspects associated with the integration of inverter-based resources into modern power system. The journey of organizing this GIAN course has been the result of nearly 2 years of meticulous planning and collaboration. The course is conceptualized with the growing need to understand the address the challenges posed by large-scale integration of IBRs. I express my sincere gratitude to Professor Sukumar Kamalasadan, who is the international faculty of this GIAN course and Professor Department of Electrical and Computer Engineering, University of North Carolina, USA, who accepted our request to collaborate and write such a good course proposal. His dedication and continuous efforts plays a pivotal role in the preparation and timely submission of the course proposal. Thank you, sir. I would also like to extend heartfelt thanks to Professor Asheesh Singh, GIAN coordinator of this course, and Professor G.P. Sahu, local GIAN coordinator of MNNIT Allahabad, for their constant support and guidance throughout the planning and execution of this course. In the post-COVID-19 era, the majority of academic courses are being conducted either in online or hybrid mode. However, this course is approved to be held entirely in offline mode. This course will not only strengthen the academic ties between MNNIT Allahabad and the international export under the GIAN framework, but will also mark a significant step towards re-establishing rich interactive academic experience in a post-pandemic world. It is expected that the knowledge gained throughout this course will inspire future research innovations and the development of advanced technical competencies in the rapid evolving energy sector. The course objective has been set by our international GIAN course coordinator faculty, Professor Sukumar Kamalasadan, and us. So there are 5 specific course objectives that will be covered under this course during next 5 days. This GIAN course includes total 20 hours lectures and tutorials hours. This course carries a weight of 1 academic credit. At the end of the course, an examination will be conducted to evaluate the participants' understanding of the concept covered throughout the sessions. Upon successful completion of the course and evaluation, each participant will receive a grade sheet as well as a certificate of participation. But for that, their attendance is mandatory to attend all the sessions. So I request all the participants to attend all the sessions actively. Now, for this particular course, total 61 number of participants have registered from different institutions across the country, in which there are several faculty members, PhD scholars, PG students and UG students. We extend our sincere thanks to the Ministry of Education, Government of India, for supporting such initiative through the GIAN scheme, and IIT Hyderabad for making all the efforts to coordinate the same. We also express our heartfelt gratitude to our Honorable Director, MNNIT Allahabad, and the Head of the Department of Electrical Engineering for their continued encouragement and administrative supports throughout the planning and execution of this course. I hope that all the participants will be extremely benefited with the content to be delivered during the next 5 days on the very relevant scheme of the power sector. I hope your active participation in the course and wish you a very best for the same. I once again thanks to all for joining the inaugural session. Thanks. Jai Hind.
Thank you, sir. We now have the privilege of hearing from local GIAN course coordinator of the institute, Professor G.P. Sahu, sir, who has played a key role in facilitating this academic collaboration. Sir, we welcome your words.
Thank you very much. I think Garima you are. Good morning, all present here. I can no. I wish to welcome Dr. Sukumar present here. So just yeah. So Professor Sukumar, Professor Risha Negi, head of the department, Professor Asheesh, coordinator of the program, and Dr. Prashant, my other senior colleague present here, Professor R.K. Singh sir, Professor R.K. Tripathi sir, Rajesh Gupta, Professor Rajesh Gupta, Professor Nitin, Dr. Deepak, Dr. Vishal, and there are many other colleagues. I welcome all present here, all the participants. Without your presence here, we could not have conducted this program. So welcome you all, and my technical team members who are putting their effort to make this program available to all others who are taking interest in the program mentioned here. I'll briefly tell you about the GIAN and its initiative or the objective. So the GIAN program we started in the year 2016, and it has completed almost 9 years of its journey. Since beginning, I'm associated with this program. We started this initiative in 15. Of course, the first program took place in the year 2016. And that point onward, of course, our institution is doing good in terms of the number of programs being organized. I think this is the 48th number of programs. So 47 programs we have already conducted at this institute, and this is the 48th. And electrical engineering department has also contributed a lot in increasing the number of programs that is being. I think it is fifth program, madam. So fifth program we started with Professor R.K. Singh's program, Madam Vinita and R.K. Singh, and then Dipayan also you conducted one program recently. So this is the fifth program in the institute. I'll briefly tell you about the in country how we are doing. So in country, we have already conducted 1,848 number of programs being already conducted. Okay, so that's a big number. You can think about how much money being spent in such programs being conducted, where we could invite 1,654 number of foreign expert. Okay, of course there are certain number of experts who have repeat visits are also there. So therefore, this number comes out to be 1,654 number of foreign faculty visited. So the conduct of this program is multiple objectives are there for conducting this program. It is not simple faculty development or refresher program kind of thing. So here we are getting foreign faculty in place, and then with the foreign faculty there are multifold objectives to be achieved. One, of course, is teaching learning. So here the teaching taking place in the current and emerging area, that's a keyword here, that it is not normal area. No, we are not learning power systems or any other subjects related to our course curriculum. So very specialized subject being offered here, and for that specialized subject, the foreign expert is the authority in entire globe. So that way we select the foreign faculty, and then we request them to conduct such program where we are able to develop expertise in the current and emerging area, so that new course curriculum and then course offer can be given. So that is one objective. Second objective, of course, we get network. Okay, so network is important here. The keyword, that global initiative on academic network. So academic network is another keyword here. So that way, we are getting opportunity to interact with foreign faculty, and participants are coming from different pan India, all the parts of the various institutions that they are visiting here. So it is multifold networking has to be done, networking with the foreign faculty, networking among yourself, because you also take interest in the common interest area is there, that's the written here. Okay, so that way foreign faculty interaction has to again go beyond one-to-one interaction. You can think about interacting with foreign faculties institution, and then your institution interaction with foreign faculty institution, our country interaction with foreign faculties country. So that way snowball kind of you need to keep on rolling up, and then bigger network can be created in the area what we are addressing here. So that's an opportunity I must mention here, that 5 days time you are going to spend with foreign faculty. So within this period of time, you need to build up rapport, establish network, and then continue, take it forward. Okay. I'm sure the coordinators of this program, they have created a WhatsApp group. So WhatsApp group also plays an important role. Okay. So that way it is not that 5 days program over WhatsApp group is deleted. No, we'll continue to have that WhatsApp group, because all of you are coming from a common interest area. So you'll keep on sharing what update taking place in the emerging area that you are talking about, or what knowledge, or how you're sharing the knowledge acquired here to your institution, your students, curriculum development, laboratory development. Those things also is going to be, of course, helpful. And then foreign faculty and our institute faculty will be able to guide you, further extend some support in case needed, in developing laboratory, in developing course curriculum in this area, on conducting research. Some collaborative research opportunity may also be there with the foreign faculty and local faculty in this institution. Now, one more important thing is that in physical mode we are conducting this program. So, of course, head of the department will tell you about the infrastructure available in this department. At the same time, make it a point that you visit the infrastructure available in this department, including the institute infrastructure, and take share your feedback about how we are doing, and then what other things can be done so that some value addition can be made. And the knowledge that you take it to your institution, your respective places, there also can be replicated, and some value addition can be done in terms of your research, in terms of laboratory development, in terms of collaboration, in terms of publication, collaborative research, proposal writing, etc. So that way, another important thing is here. One more data I wish to share among the all of us know that we have number of NITs and IITs in our country. So in terms of number of programs being organized in IITs and NITs, I have the figure that NITs have organized 462 number of programs. So I mentioned that around 1800 programs out of 1800, 462 being organized by NITs, and we have organized 48. So that way you can calculate that among the NITs also we are doing good in terms of number of programs organized. Okay. So that way it is, I'm thankful to, of course, Ministry of Education, and the nodal agency in our country is the Indian Institute of Technology, Hyderabad. So their support is excellent support we are receiving from them, and on a daily basis, on hourly basis, on phone call also, they are all the time available to support us in terms of funding, budget, invitation, some delay in the program, extension of the program. So that way, okay. So I wish to close here. I'm thankful to the coordinators that they have provided me this opportunity to talk to you all, and I wish all the best to the coordinator for successful conduct of this program. Wish you all the best. Wish you happy learning, happy stay in our institute. Thank you very much.
Thank you, sir, for your kind words. I now invite Head of the Electrical Engineering Department, Professor Richa Negi ma'am, to address the gathering and share insights on the significance of this program. Ma'am, please.
So on behalf of Electrical Engineering Department, I welcome Professor Sukumar Kamalasadan, our foreign expert for this GIAN course, and the course coordinators of this GIAN course, Dr. Prashant Kumar Tiwari and Professor Asheesh Kumar Singh, and also the local GIAN coordinator, all the faculty fellows and the participants. So just as this local GIAN coordinator, Professor GP Sahu sir said ki head of the department will be telling you about the infrastructure of the department. So we have got very well equipped labs, and as this course is on modeling management of inverter-based integrated electric grid, so we have got well equipped power electronics lab, power system lab, machines lab, control systems lab. So for the participants who have come from outside from this institute, they can go around the department and have a visit to all the labs. And I'll request all the lab OCs to provide all the available facilities and knowledge to these participants, and make them aware about how these labs function, and what are the list of the experiments in various labs.
So this is the lab thing, and rest is the seminar hall. This where we are holding this program GIAN course, and within 5 days, you can go around and have a visit and have a look of the department. It's a small department, compact department with good human resource, good faculty resource, and if you want to collaborate with any faculty, all the faculty is available are available in their chambers. You can go and interact with them also, and I hope some good outcomes will be there from this collaboration with University of Carolina and MNNIT Electrical Department of Electrical Engineering after this completion of the course. And the participants will be benefited from this 5-day GIAN course. And as Professor G.P. Sahu said, this is 48 of the college. So let's proceed towards the century. And I'll request my young faculty members to come up with new GIAN courses and apply. I think, sir, call is open. So they can collaborate. They all have come. They all have done PDF. They have got their links. So please use them. Write GIAN courses. Make collaborations. So with this, I end. And congratulations to the team. Thank you. Thank you, ma'am. Now, before inviting our expert, Professor Kamalasadan sir, I request Ms. Mahima to give the brief introduction about Professor Kamalasadan sir.
Dr. Sukumar Kamalasadan sir is a professor and distinguished scholar in the Department of Electrical and Computer Engineering at University of North Carolina at Charlotte, USA. His research interests include smart grid design, renewable energy integration, power grid modernization, real-time modeling and control of energy system and devices, energy storage, and wind energy modeling and control, and microgrid management. Professor Kamalasadan's research for the last 21 years has resulted in tools and methods that have a high-level impact in electric utility modernization, with a fleet-wide deployment of his tools that enable modern grid management and control integrity, renewable energy, and energy storage. His research work has secured more than $15 million from the US Department of Energy and National Science Foundation, Siemens Energy Research, Duke Energy Corporation, and several other industries. He is a chief architect of Duke Energy Smart Grid Laboratory at UNCC and has secured about $5 million facility. He has published more than 300 papers and has supervised 36 PhD students, 30 MS theses and projects, and more than 60 undergraduate projects. He has about 25 years of teaching and research experience. He is a recipient of the National Science Foundation Career Award and 12 IEEE Best Paper Awards. He received the Outstanding Research Award in the year of 2021, Struck Gold Medal Award in the 2023, both from the UNC Charlotte. He is a distinguished lecturer of IEEE Power and Energy Society and Deputy Editor-in-Chief of IEEE Transaction on Industry Application and past chair of the Power and Energy Education Committee and Industrial Automation and Control Committee. He has delivered more than 50 talks including keynotes and panels for IEEE sponsored conference. It is an honor to invite our foreign expert, Professor Kamalasadan sir, to deliver his address. We are truly privileged to have your presence and expertise, sir. Please, sir.
Thank you. Thanks for the introduction. Respected faculty members at the dais, eminent senior faculty members sitting here, the learners, the student side, and the other faculty group, which I gather that they're also here for learning. First, I would like to thanks for inviting me to have this opportunity to deliver this GIAN course, at the MNNIT. I gather from Professor Sahu that the number of courses that's been organized here under MNNIT in GIAN and other form, it's it's more than what I can see in any other institutions has been organized. So first of all, I would like to comment on the dedication of the faculty member here and all the group which has been organizing this. Congratulations on that. I hope in next 5 days you will be able to learn or have exchange ideas, especially on this topic. One thing which I wanted to mention specifically, what Professor Sahu has already mentioned. Please pay attention to the detail about the title and the course. It's not just a generic course content that we are delivering under this GIAN program. It's a modeling of electric grid, which you may think that it is kind of generic in the first course in power system and so forth. In the department, we learned that. But here, the idea is integrating IBRs or inverter-based resources. So having said that, you may want to think while you're attending the course, what is the difference? Why, if we integrate in inverter-based resources to the power grid modeling, how do we make the operation of the power grid efficient in terms of reliability, resiliency, as well as the stability of the electric grid if the inverter-based resources are integrated? So just please connect with the details with respect to what happens if the electric grid is integrated with inverter-based resources. So that's basically the content. So we would like to hopefully we'll get a chance to brainstorm the differences and an aspect related to that. Second, I want to also mention that the course content that we have been talking about for the last 2 years, the dedication from the course coordinator, Dr. Tiwari and Professor Singh, for continuously engaging with me and then refining the course content. So a lot of background work has gone into developing this course. So I hope you will see that in the content and in the title or in the course while I deliver. So I would want to comment on their dedication as well. Last, I would like to, I hope that you all will have a very brainstorming session on the different level. I will try to teach the course, which I gather that we have quite a bit of undergraduate in the course, registration as far as learners are concerned. Quite a bit of postgraduate course, master's level students also included, and also the PhD. So I think it's a vibrant group of audience, which I will be, taking care in the next 5 years. I'll try to deliver the course in that, all the 3 different levels. But if you have any questions or any thing that comes in your mind, we always say in the academic world, no question is a bad question for academics because we want to impact you in your learning aspect. So any questions to come in your mind, anything that you wanted to discuss, please feel free during the course, and then hopefully I'll be able to take care of you. Thank you.
Thank you, sir, for your kind words. We now come to the vote of the thanks. For this, I request Dr. Prashant Kumar Tiwari, sir, to kindly express the gratitude to all those who made today's ceremony possible.
Again, I thanks to all the dignitaries on the dais and other faculty members, participants, and other members of the dais. First and foremost, I would like to thanks our Honorable Director, sir, for his guidance and all the necessary supports to organize this GIAN course. I would also like to express sincere thanks to our experts, Professor Sukumar Kamalasadan, for joining us from the University of Carolina, USA. We are honored to have your association with this GIAN initiative and look forward to your invaluable lectures and interaction during the course. A special note of thanks to Head of the Electrical Engineering Department, Professor Richa Negi, for her constant support and leadership, which made this event and course execution possible. Thank you, ma'am. I also thanks to our local GIAN coordinator, Professor G.P. Sahu, and course coordinator of this GIAN course, Professor Asheesh Singh, for their continuous guidance and support throughout the proposal and implementation stage of this course. Thank you, sirs. I extend warm appreciation to all the faculty members, staff and students whose efforts behind the scene have contributed to the smooth organization of this course. I thanks to our participants both from within and outside the institution for your keen interest and enthusiastic participation in this GIAN course. We are confident that the planned sessions over the coming days will offer deep insights or open new avenues of learning and collaboration. I also extend my gratitude to the Ministry of Education, Government of India and GIAN team IIT Hyderabad for giving us this opportunity to organize such a valuable and globally connected academic event. Last but not least, I thanks to our student volunteers team, Naresh, Mahima, Arun, Ayushi, Devans, Akash and others who worked day and night to make the event successful. I also thanks to our GIAN webcasting team who have worked and a lot to make this course online, and live streaming is going on through their efforts. Thanks to the team. With these words, I also thanks to all those who have supported directly or indirectly for organizing this GIAN course. Once again, I thank you all for joining us today. We look forward to a fruitful and enriching learning experience ahead. Thank you. Jai Hind.
Thank you, sir. As we approach to the conclusion of this ceremony, I request everyone to please rise for the national anthem. जनगण मन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड़ उत्कल बंग विंध्य हिमाचल यमुना गंगा उच्चल जलधि तिरंगा तब शुभ नामे जागे तब शुभ आशीष मांगे गाए तब जय गाथा जनगण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे. Thank you, everyone. With this, we conclude the inaugural ceremony of the GIAN course, and we look forward to the fruitful academic journey in upcoming 5 days.
Please come for the group photo. All participants and faculty, please come for the group photo. Everyone, please rise for the group photo. I invite you all to join for a refreshing tea break session outside the seminar hall. We will reassemble at 11 a.m. sharp for the first lecture of the GIAN course. All of one, please reassemble at 11:15.
तो वहां से हो जाएगा सर, शेयर वहां से हो जाएगा, वो जो सर ने बताया भी 11। अच्छा, वो केवल ऑनलाइन के लिए है।
One thing I would like to inform to all the participants, at least 90% attendance is required for appearing in the examination, getting the certificate. So please be there in all the sessions actively. Thank you.
Welcome back, everyone. We now begin lecture 1 to be delivered by our esteemed foreign faculty, Dr. Professor Sukumar Kamalasadan, sir. Sir, we are eager to learn from your vast experience. Please, sir.
Okay. Can you hear me over there? Okay. So good morning, everyone. So what we have done, how we have planned this course is like you see in the title, the course is Modeling and Management of Inverter-Based Resources Integrated Electric Grid. So there are two parts there, as you can see from the title. One is inverter-based resources, and the second one is integrated electric grid. Integrated electric grid sounds like inverter-based resources integrated or electric grid integrated, because in the electric grid we have normally talks about electric grid transmission system and electric grid distribution system. You may be aware of that, right? The electric grid is kind of, if you look at it, can be divided into parts, transmission network and distribution network. So electric grid is one part, and then IBR, okay, and then connected together. So I was just mentioning to professors, the IBR, when we talk about inverter-based resources, there are parts in the IBR. One main part that in the inverter-based resources that we electric grid interact is inverter. So if you look at inverter-based resources, there is a source, then there is some power electronics devices, then come the electric grid. So if you say inverter-based resources, it consists of source, and then power electronics and grid. And power electronics part, that as an electric grid person is more interested is a power electronic device called inverter. That's why it is called inverter-based resources, right? So power electronics, so you may ask the question, oh, okay, so is there any other things in power electronics? Yes, you have other devices in power electronics, which you can call as a rectifier or some other ways. Basically what it does is changing from one form of, source side where it is DC, in the case of inverter, to AC, right? So that's why the word inverter-based resources, because as a power grid person, you kind of don't care about other parts other than inverter, because inverter is the one which is connecting the power electronic side to the electric grid. So that's why this name came into being. So you may be wondering why. So it's generally called inverter-based resources because inverter is the one which is the key connecting the power electronics, or rather connecting the DC side sources to this. So if you talk about this, then this meaning this course especially, we are focusing on modeling and management, right? Modeling and management of electric grid with inverter-based resources, right? So like I said at the beginning, how we planned this course is we will start today to talk about electric grid first, and then we talk about electric grid, how the electric grid needs to be modeled or changed from conventional modeling to include inverter-based resources. So that's the first part. So we'll talk about that today. we'll talk about how we do that from the electric grid side. So we will not, we will conveniently say how you need to represent inverters for electric grid modeling, and very in a light form, basically how the electric grid sees when the inverter functions. And then slowly we will start looking into the details of modeling of inverters as well when they progress, maybe the second day, third day, and depending upon that. So with that, are you following what I'm saying? Okay. So with that, just to give this pulse on the audience, how many are doing undergraduate program, undergraduate studies, UG? UG. Okay. And in this UG group, have you taken one course in power system? How many have taken one course? Okay. And how many have taken no course in power system? No idea about at all power system. I don't know nothing about power system. How many? You should write no. It's not all required for me to understand. 3. Okay. How many have taken at least one course in power electronics, like inverters? Okay. How many have taken no course in power electronics? No idea about power electronics? 2, 3. So for the group here, I think 3 or 4 who don't know about power systems and power electronics, whatever I'm talking about, suppose it's not it's too much for you, please raise hands and ask the questions. To make this move forward, I may have to tell you, we'll talk about later, but that's okay, just because of time. And then I will in offline talk to you about how to enrich your experience. Otherwise, you will be too out of context, right? So that's the reason. How many in the master's program? Masters. Okay. Yeah, any masters, power system, all are power system masters. Anybody in all are power system. Okay. How many in any master students in power electronics? Or power systems. I'm asking this because I will have to talk about power electronics. So I have to. So all the students in the master's program, you have taken one course in power electronics? Some basic idea about power electronics? If no, and raise hands. If yes. Okay. PhD scholars, how many? And you have, power systems and power electronics, I guess, basics. And then I will try to enrich your experience. Faculty members, I'll try to enrich your experience. Maybe I'll learn from you, but I'll try to enrich as much as I can and just try to connect some spark, some things which you will enjoy. Oh, I see, I'd love to, something like that, but beyond maybe. So that's the kind of, so we will talk about mainly power system today, basics of power system in this part, first part. And then I'll talk about a little bit about how do you model the power system on what we call it as steady state condition. Do you know what a steady state means? Steady state means normal operating condition. Like you are in a car, you are we tell in the US called cruise mode, meaning you press the button, you are like no problem, nothing is happening, roads are good and no stop, and so that we call it steady state. Steady state meaning you do not expect any changes. Okay, in the steady state, unfortunately, electric grid, there is nothing called steady state for electric grid, because every time the load that is connected to the electric grid is changing. So the generation of the electric grid changes. So such changes in general, we call it ambient condition. Ambient means normal ambient condition. Okay? So those changes in the electric grid sense, for an electric grid, we see like a noise. Everybody know noise, right? Noise is something which is not good. For electric grid, it is good. The change in the load is some small changes. Okay, so those small changes, what happens? Why we call it noise? Because that's not very big. So you still go with the same change load generation, balance. That load generation balance condition is called steady state. Okay, so first time when you model an electric grid, there are two words there: model and management. Okay, when you model an electric grid, first model for an electric grid is to make the model of the electric grid perform during steady state. Okay? You cannot model anything if you cannot model steady state. Right? So that model of electric grid is required to understand how the electric grid runs in steady state. Okay? So you may ask the question, I don't know whether you are aware of this or not. Why do you model anything? Oh, models are basically mostly on electric grid originally, and it starts with mathematical models. Okay. Is there any other kind of models other than mathematical models? Yes? No? Oh yeah. What do you mean by physical model? How do you get a physical model? Physical model is it's existing. Okay. So why you call physical model? That's the physical system. Why? Because it's the same. It can be like this. We have actually granular circuit up here. Why you call it model? Model is actually so the model means that it is a representation of the real life. That's why it's model. So if anything that you physically develop or design is not the real, but a representation of the real is called model. So for example, if you develop if you want to see a 1 MVA, I'll still go back to some interesting power lecture. I'll still start going. So it's an inverter. It's a 1 megawatt inverter, 1 MVA inverter standing there, real life, physical inverter. But can you represent the inverter using a 1 kW system, physical? That's called model. But representing means what? Representing the characteristics of the real device is what the model does. So there are physical models. You're right, spot on. Physical models are, So now you may call that, is it really a model or is it a prototype? So you may hear people, professors telling you, okay, make a prototype in the lab. What is the difference between prototype and a model? I don't want to digress the talk, but I just wanted to see you some. They are different. Anyway, so I'll talk about what's the difference in sometimes when you talk, while you work on it. So the models are actually representation of physical model. Any other models? Scale down model. What is product? That's scale down model. Okay, well, exactly. Yeah. So we'll talk about what are the differences in prototypes. Okay. Yeah. Since that broad prototypes are scale down models means what? Either representing the characteristics fully of the real system, but it's still not at the reach the level of models that you can call that as a real system. But they are whatever scale, you call it lab scale or, different levels of scalability, right? Some are not scalable. So what happens if you have a model or a prototype sitting here, which is not scalable? Is that a good representation of a physical system? No, right, because it's not scalable. You're not right. So what is important there? Since you brought that up, it's important also to understand the model that represents the physical system, right? At the end of the day, the characteristics of the physical system, it also should be scalable. Okay? So idea of modeling is actually not just developing something. So how do you know that it represents the characteristics of the physical system? How do you know the model is scalable? There are some specific checks. First check is you look at a physical system, you run an operational test on a physical system, you put an input, you get the output, you can collect the input-output information. It can be input-output characteristics or input-input characteristics, whatever you want to do in the physical system, collect that data. Then you go to your model, you run the same, and then you compare, match, see whether it's operating same as well. That's one. So if you develop a model, it has to represent the characteristics of the real physical system. If you develop the model, it has to be scalable. If you develop the model, you have to run some tests or experiments on the model to make sure that it is doing the checks and balance. And one test is characteristics of the real system with respect to the model. What is the second test for scalability? What do you do? Well, you got to perform test with respect to the scale of that model. So if it's a device, what is a scalability test? You interpolate that model to perform on a higher power capacity, for example, or a higher voltage level capacity, and then you do a test to see whether it's scalable. What do you do with a power system model? Our system is system, right? Models are, there is another modeling difference. One is a model of a physical device. Another is a model of a system. Modeling of the system is a little bit different. Modeling of the system has models of physical devices inside the system. So like 7 physical devices in the system. If you want to model a system, you have to model all the 7 physical devices, right? And then you bring up the model of the system. So how do you know the scalability of the model of the system? By performing the test on the model of the physical for models of that physical system and increase the number of parameters or variables on the physical system. So in a power grid, scalability is tested by testing these models running on number of points on the power grid. Number of points on the power grid is generally called as nodes, okay, or buses. Okay, what's the difference between a node and a bus? I think you are actively participating. Other people on power system. What's the difference between a node and a bus? If you do, it's not even power system. If you do an electric circuit analysis, you do something called nodal analysis. Have you heard of nodal analysis? Okay. What is a nodal analysis? What is a node? Two or more number of points that is connected on its two physical device that you have. If you have a physical device, you always call this has got a physical device can be represented as a 2-port network, which means input and output. So this device, another device connected together, that point is called node. Good. So you node voltage analysis. You take this node and then you do analysis. Analysis of what? Voltage. Node voltage analysis. What do you analyze? Voltage of the nodes. How do you analyze voltage of nodes? It's a different story. We'll talk about later. So it's node voltage, node analysis, right? Node. What's the difference between node and a bus? More or less? What's the difference between a node and a bus? PhD scholar, you're back. You know this all. What's it? Huh? Processor? Yeah. Collection of nodes meaning, suppose there are 3 nodes. All the 3 nodes collected together will become a bus. Actually, it is yes. But that nodes has to be at the same point. Can I have one node in one point, another node in another point, connect them together and call a bus?
Yes.
You cannot. So let's have a bus, right? One node connected to the bus, another node connected to the bus, third node connected to the same bus. Then it is a bus, collection of 3 nodes. One node here, another node here. That's not bus. There are 2 buses, different buses. So buses are one or more number of nodes at the same point is called the buses. Okay? How well will that happen? It will only happen if you have 3 connecting points or 2 connecting points or 1 connecting points coming together. Okay? In an electric grid, is operated in what we call it 3 phases or 3 connecting lines. Okay? So if these three connected to one point, there will be three nodes made by these three lines. And that three node, we call it as a bus. Can the two lines connected to one point is also called as a bus? Yes, it is also called as a bus. It's a two node bus. Can one line connected to one point, which is a node, can it be called as a bus? Yes, it is a bus. It's a node and the bus. But generally, you call it node. You don't call it separately as a bus. So you see the difference between node and the bus? So the node and the bus will only happen in electric grid because you have more than two lines or three lines connected, right? But this is generally represented for a three connected nodes in electric transmission system or a bulk electric grid. There will be three lines connected together. On a power distribution network coming to your home, sometimes you will have one node, right? One phase or two phase, two nodes, right? So such things are called nodes. I'm saying this because you will hear in what we talked today, model of electric grid, buses and nodes coming in. So nodes, you can say, representative for electric distribution system. You will have two nodes, one node, things like that. In electric transmission system, we call it as buses. Are you all following? That making sense? Yes. Okay. So electric power system, when you talk about, you connect these devices together to form a system, and you represent the scalability of the model. That's what the story you were. Okay, scalability of the model by testing these parameters on a scaled system, which is represented by buses or nodes. So an electric grid is a representation of electric grid. How many nodes in your electric grid? Electric power engineer talk about that. So that kind of spark to socialize. Say, how did you test it? Did you test it on how many nodes? That's actually to test the scalability. Oh, I tested it on 3000 nodes. Oh, wow, that's good. The model is now very good. Is there an end to it? There is no end to it. I can test it on 30,000 nodes. Characterization says that if at a good level of node testing which you do or bus testing you do, it can scale up to higher level of nodes or higher level of bus so that you can run it on a real system. I don't know the numbers in India. I have not gotten myself educated with it, but in the eastern side of the United States has got 30,000 buses. That is one section of the United States. So if you want to really implement your models on a real system and do some test on projects coming from DST or also large scale project and showcase to the country that, well, I built a model and that's real. I can test it on real. You may want to scale it up to that level and test it. So what we learned so far? We learned about models. We learned about the difference. Why do you want to do models? We learned about what type of models you do first in an electric grid, steady state condition. We learned about the models that you do in electric grid consist of devices, and the device models on the electric grid, collection of them together, you represent that on the electric grid modeling. Testing the model, you test it quickly writing. These are not in the slides, by the way, so if you want to write it down, you may want to. I'm just still trying to set it up. So when I show you on the slides, you will know why this is coming. Otherwise you'll say, stuff we did. I don't care. I don't know what is going on. So we don't want that. That's why I'm setting this up. So you have models, which is, devices connected. These models are representative of the real system. There are other type of models called physical models. Is there any other type of models other than physical model? I just want to say that too, because it will come at some point of time. There are models which are not really representation of physical models. So for example, suppose you want to find a model of a real system, but this model is not possible to make mathematical model. Okay, is there a situation in which you cannot make a mathematical model of a real system? Or everything can be done through mathematics?
System complexity becomes very high. We want to reduce the order.
If you have a system that is very complex, okay, you cannot necessarily make a model. How do you assess the complexity? What do you mean by complexity? How do you assess the complexity? in terms of resource requirement. Complex systems are not dependent on the resources are actually inputs or things on the system, right? Complexity of the system means the system behaves in different ways at different times or different conditions. Okay, so if you capture all those behavior into one representation, it's hard for you to develop such techniques or such bases. So for example, I'll give you one simple example of what we call it as nonlinearity. So if you look at a device, a very small device, diode for that matter, any nonlinear device, not the linear device. Some devices we model represent as a linear device. So if you look at a diode for that matter, it has got nonlinear. You know what a nonlinearity means? What's a nonlinear characteristics of behavior means? If you apply an input to the system, when you look at the output of the system, for example, input-output, nonlinearity, the output is not linear to the input. If the output is linear to the input, you can represent the linear model in the form of mathematical model using linear equations. The output is not representative of the input. What do? You have to represent nonlinear equations, right? For representing a nonlinear equations, it's not that easy. What happens if this device operates in different characteristics in different regions and you want to capture all of it? Well, then you are having the mathematical complexity increases. What happens if this device behavior changes with respect to conditions? When the weather pattern changes, the behavior of change. So then you say, oh, that's uncertain. It's not very certain what this. So you have to represent uncertainty of the device. You have to represent some ways to find out which point the system operates in an uncertain behavior. All these things are nuances or changes that you have to make on the modeling side to represent a system which operates in different ways. So or device. So you can say, oh, it's a very complex device to model. That's device complexity, not the input, number of inputs increase or number of output. Do you have a complexity in the number of inputs and number of? Yes, you too can actually have 7 input that has to go into this device to model this device. 25 input that goes into the model. Again, that's a different level of complexity. I'm talking about device complexity. So complexity in general, you can call that whatever that level which you have. So the modeling is actually dependent upon that, and mathematical models are related to mathematical tools that we get. And we are not mathematicians. As an engineer, what you do? You borrow the tools that is developed by mathematicians and try to sneak in and get and do some art to make this model of electric grid work on that. You don't originally develop. There are some mathematical sciences you develop looking at the physical system, but that's what you do in general, right? That's mathematical. So what happens if you cannot do mathematical model at all? Then you utilize model development based on operation of the a real device, looking at the data. So you put an input to the device, some bunch of data, you record the data, and then you look at the output coming from the device, you record the data, and then you do an input-output mapping. That mapping can be done through, for example, an Excel spreadsheet, and you put a regression equation for the represent non-linearity or anything on the device. Such models are called data-driven models. You can also call that as a some gray box. There are, I don't know whether you know the difference between white box model, gray box model. Again, that's a we talk about that at some point of time. But generally, they are data-driven. Okay. There is also something called data-induced. And there's a difference between those two. Shown and induced, both are not the same. So that's why I'm saying that in this course, which I wanted to bring in all these nuances, so smaller changes, which otherwise you don't know what you're doing, in general. Anyway, so you understood the models, right? These are different type of models. Having said that, now probably we can pick up the pace and you will understand what we are talking here. So today, main job is basically to bring you an essence on what? How do you model a system or a device? How do you model an electric grid system? Number one. Number two, How do you model the electric grid in steady state condition, operating condition? And how do you, on that very light or rather modeling part on IBR side, and sprinkle or tell you how to model a very baseline representation of IBR. And when you do a baseline representation IBR, we'll talk about baseline representation just inverter. How to model that. So that's our goal. Good. Many of you, I will start from the fundamentals. So once I start, from fundamentals, you can hear me with this, right? I'll speak up a little bit. This will induce more noise, which will not be ambient, and it will be tough for us today. So in the modeling, what we will focus on is just the electric grid model. Many of these electric grid model you may know. If you don't know, you may want to. If you don't know, you may want to raise hands and stop me. Then I will tell you what will be the difference in modeling of electric grid when you consider inverter-based resources. Am I going too fast? How many of you think I'm going too fast? Is it? Am I going too slow? Good. You understand what I'm talking? Okay. All right. So, so I just wanted to get some honor of few research students which helped me build different aspects which I'm talking here. 3 of my research scholars. So the motivation of this modeling is all related to one specific thing about inverter-based resources. Okay? Inverter-based resources are coming to the electric grid. Why it is coming to the electric grid? Why inverter-based resources are there in the electric? Anybody? You don't know? It's there, so I'm happy and I'm doing something right. Do you know why they are there? So it's actually related to renewable energy integration. Renewable energy integration in the electric grid is because of 2 reasons. What? Number 1? Environmental aspects in renewable energy based inclusion reduces, for example, carbon emission because they are not fossil fuel based. That's one. What's the second one? Yeah. So it's actually also to do that. So these 2 are the main part, renewable energy. So as a power engineer, you really don't care much about inverter or inverter based resources. However, then why do you want to, if you are worried about renewables, why you want to talk about inverter based resources? Because most or the 2 mature renewable based technology that is connected to electric grid comes on connected to electric through inverters. One is photovoltaics. Everybody know PVs, photovoltaics. It actually generates the power in DC, and then you have to connect it through inverter. Second mature renewable technology, mature wind. So when I was a wind, then that's why I was just wind connected to the inverter. Not necessarily, but wind is connected to the electric grid through back-to-back inverters. AC, DC, DC to AC. Why you use inverter? Why cannot you connect the wind directly to the electric grid? Because of the wind speed is not constant or synchronous. But since it is not constant or synchronous, you have to make it to a constant speed, which can be done through this magic device called inverters or power point device. Why they are magical? Because they take that speed and convert that into frequency and then work with all this magic frequency and bring another good frequency at the end. And that's constant. So that's why in the wind farms or wind to mature technology uses inverter. So it's basically inverter based. Okay, so this is good. So because of that, future power grid are expected to increase a large number of inverter-based resources. Okay. Inverter-based resources comes in two forms. Inverter-based resources is connected in a one specific location on electric transmission network that we call it centralized, meaning at one location you have inverter-based resources. Very minimum such resources are very minimum in the electric grid so far, because it requires a vast area of land to have an inverter-based resources at that scale to develop. Okay, so much of the inverter-based resources are also spread out in different areas. Okay? Such inverter-based resources which are spread out, or non-inverter-based resources which are spread out, are called distributed energy resources. Okay? So you will invariably see people talking about DER, IBR, all these acronyms. I don't know what's going on. That's because it's a distributed. So these distributed energy resources must be from inverter? Not necessary. You can have a distributed energy resources which are non-inverter based. Okay. What's an example of a non-inverter based distributed energy resource? Any small hydros are non-inverter based distributed energies. How about diesel generator? Diesel generator, which is running on a diesel, is you can take that box and put it anywhere, and it's non-inverter. So you got it. Why I'm asking these questions? As far as anybody, any learner for that matter, especially when you are a deep learner called researcher or a light learner called hobbyist, everybody needs to think about why and what. Do not worry about how I do this or what software I run. So I'm just trying to do my best to ask this question. So DER, that's the difference between distributed energy resources. There is also the term that you will see called RER. RER are renewable energy resources. Okay, renewable energy resources. Can the renewable energy resources without an inverter? So you may ask the question, RER. I thought that's IBR. So why do you want that? You have a renewable energy resource without inverter. Same hydro. It's renewable. Hydro energy resources are renewables. Hydro resources are renewable. So that's renewable. If that's a central renewable, not distributed, you call it RER, right? I mean, you can call it central or distributed. RER is a general term. Renewable. How about nuclear? Some people say nuclear energy resources are renewables. And nuclear is actually renewable, except for the waste related challenge that's associated with renewables. And there are renewables that is now coming up, especially in the US, maybe in India too. They call it small nuclear reactor or SNR. Small nuclear reactor means nuclear reactor in a small scale, which can be connected into any areas. So there are people who was trying to develop small nuclear reactors. Okay, so how do you so we talked about models of electric grid, models of the electric grid in steady state. Are you writing down, right? Models of the electric grid in steady state. What will you do with the model of the electric grid in steady state? What will you do with the models of electric grid in steady state? Okay, models of a device in steady state. What will you do? You use it for what? You use it for checking the operational characteristics of the device. We remember that we mentioned. So you must say, what operational characteristics I will check if it is steady state? You check what? One operational characteristic that you can check for a device. Power rating or capacity. Is this something, for example, inverter? Okay, 1 MVA inverter. If I give 1 MVA or rather power that is drawn from the inverter is 1 MVA, will it really work? Or will it collapse? That's what you call it, capacity test for rating the capacity, which is normally done there in the undergraduate lab. We call 3 different type of tests that you perform in a first energy conversion or machines course. What are the 3 tests that you do? Have you heard of no load test? Have you heard of no load test? Yes? Okay, what do you do in a no load test? You take a device, do not connect any load to the device, and you run the device. Why do you do a no load test? What will happen if no load is connected? You just check the no load losses on the device. You also check another thing on no load test. What is that? Huh? You look at the voltage, output voltage of operation. You cannot check the current flowing through the device in a no load test. Can you? No. So if you cannot check the current flowing through a no load test, how can you check the losses in the no load test? There are some part in the device which is consuming the current, which is not going out. That part of the device which is consuming the current will generate some losses, and you are checking that loss. So no load test losses or no load losses that you talk about are the device or the parts in the device which is connected in parallel or connected in parallel branch is also called shunt, connected in shunt form. Okay, that's what the no load test is. Any other test which you do on the then you do what you call it as full load test. Have you heard of full load? There you check what? First you check the voltage, you make sure voltage is correct, then you check the current flowing through this and see whether the current can flow through that. What do you check in that? You check the thermal characteristics, ability of the device to perform very well when the current is flowing through the device in full load condition. So you can change the loads step by step and go to full load. Then what will test you do? What's the third test? Short circuit test. This is fundamental. This is UG. Everybody should be saying this. This is the thing. If you do any course in the third year, I guess, whatever the year, we have it in this, there, at least by third year, you should be doing this. So it's called short circuit test. What do you do in short circuit test? You apply a short circuit on the test, on the device. You apply the short circuit on a rated voltage, right? No, you cannot apply any short circuit on the, if you apply a short circuit on rated voltage, everything is go off. You will also go off, maybe with the machine or device. You apply a short circuit test on a rated current. You try to increase the voltage slowly up so that the current on the device increases up to the rated current. So voltage will be small. These are the kind of story that we do in a lab, it's undergrad. But anyway, so on the steady state condition, you do what? Capacity test. Okay. Capacity test in general in the electric grid is called power flow. If you want to do capacity test, especially on the full load test, you have to have the power flowing through the device. Okay. So the power flow is basically what we do on the capacity test. So that in general on electric grid is called power flow studies. Okay, that's the study that you do. Everybody heard of power flow studies? Yes? Okay. Power flow study is also known as load flow test or load flow studies. Okay, so interchangeably called load flow or power flow. Why you call load flow? You are giving a load so the power can flow. Otherwise, your load. So you may ask a question: what load will you give? Well, you can give anything. Nobody tells you that you should give one load. Necessarily, very importantly, you will give one specific load, which is the maximum load that can be connected to the device or the system to test the performance capability of the system on what we call it as full load. Remember full load test, right? That is not necessary that every time you get full load. Why do you give a full load on a power grid and do a power flow study? What happens when the load is connected to an electric grid with the power flows? Why do you want to do full load test? When the load is connected, what happens? Load current will be drawn from the source to the load. On an electric system level study, when the current is drawn from the source to the load, if the load is not connected directly to the source, the load is connected in some other node or some other bus. Now you should connect with all I'm talking about. So some other bus, what happens to the power flow? Power has to flow all the way to that bus and go to the load. When power flows to a conductor or a wire, what happens? Losses happens, and when the losses happen, what happens to the voltage? voltage on each of those nodes or the places that is flowing through started collapsing. It's actually like a water in a pipeline. So the water is full in a pipeline, you get a good pressure and go all the way up. When the pipe is clogged, what happens? Nothing comes out. What happens if the pipe is full clogged? Not only nothing comes out, water starts hitting on the side of the pipe. It may burst the pipe and it starts seeping out. Okay? This is what you call it as energy imbalance, or energy is coming in, it's not going out. Because of the energy imbalance, it will affect the one point and then it bursts. Similar thing happened. So what are we doing now? In the steady state condition for a model of an electric grid, we do what we call it as load flow studies or power flow. Are you connecting I'm connecting with the storyboard, not losing the train of thought, so that you should also go with me along with that. So what we do is load flow studies. So basically, efficient load flow methods can solve power system with DER, distributed energy resource. So when you solve a load flow study in a power grid, you may also want to talk about how the power grid is organized. Everybody know the organization of the power grid in two different layers. One is called the three-layer for that matter. One is called generators on electric grid, located at different points, connected to conductors and wires, going through a specific system called transmission system. And after the transmission system ends, it comes into a location called stations, and they are called three different names. One is called receiving station, where you receive the power, bulk power, or it's also called substations. There are stations which are many of them connected, and that substation that drives that power to the loads, which are called distribution network, which is connected to the loads called industrial loads, residential loads, and we have loads that is connected from inverter-based resources called wind farms, battery energy storage, solar farms. All these are inverter-based resources. So see the number of inverter-based resources are loads. Inverter/loads. So some consume power, some deliver the power. So all these folks are connected right there on electric distribution system. Here you model the electric grid in one phase representation of three phase, and such models are called bus models, where buses are considered as three nodes connected to one point, and you run the model in one phase representation. Okay. Ideally, electric transmission systems are not run in phase-based model. It's running connecting all three phases to one line representation, and those models are generally called positive sequence representation. How many of you heard of this word, positive sequence? How many of you heard of the word positive sequence? No, have you heard of positive sequence? No? Nobody? The sequence of primary elements. There are supply reverse sequences. There should be collected. Negative sequence. There are three invariant things. Combination of all three is related to the why do you think of the sequence? Representation actually is a representation of a system to see what is the effect when there are connected devices in that system on each phase separately. What is the challenge of connecting a device in the system in each phase which are not same? Then the current flowing through each phase will be different. current flowing through each phase will be different at this point. What happens to the voltage on each phase on this point? Will be different. Why? The drop will be different. Forgetting about other things, drop will be different. When voltage is here on this point and current is different on this point, what happens to the voltage and current? And then you do not have such things, or what we call it as unbalanced nature of an electric grid. Unbalance contributed by changes on the load on each phase. So you may ask a question, can unbalance contributed by something else? Yes, imbalance can be contributed by many factors. One factor is changes of loads in the system. But it's another thing is unbalance. What are the another part that contributes unbalance? Yeah, that's a good thing. So when we started, what models are we doing? Steady state. What do you mean by steady state models? Is that a normal operating condition or abnormal operating condition? Normal. So one thing in electric grid is a very important thing that you mentioned. One thing electric grid, whatever you do in electric grid, you want to define your scope. If you start looking at everything, they're all different. So we are not talking about abnormal operating conditions of electric grid, normal operating. When you apply a fault to the electric grid, is that going to be a normal operating condition or an applied? No. So having said that, let's park that discussion of unbalance created by fault so that we talk about when fault is applied to the electric grid. So in the context of electric grid being normal operating condition on its steady state condition, what else causes unbalance? Okay, you have 3 lines, right? 3 lines, right? Remember, 3 lines make 1 bus, or 3 lines, 3. Each of these lines is transferring power from point A to point 3, and current changes from point A to point B, and the current changes from point A to point B will create electromagnetic waves that is changing from point A to point B. When that changes from point A to point B, what happens? These conductors can affect the voltage at each point because of these changes in electromagnetic waves. That point goes from point A to point B. Okay? Such conductor-related changes affecting the current because of the inductance in the conductor and resistance affecting the current can also create unbalances on the voltages. That will only happen when the current flows. Without the current flow, these folks are just great. They will not do anything. Current starts flowing, they will behave differently. So they will create unbalances on the system, right? It is predominantly going to happen if you have the conductor which are not laid or which has 3-phase, 2-phase and single phase. So one way to take care of these unbalances, we call that you change the conductor orientation at different points, and then transmission grid, we call it transposition or transpose. Okay, that's the concept of transpose. So people may ask, why do you transpose? This is the reason you transpose. When you transpose, what happens? Your system are going to be staying balanced. 2 things which you do, you transpose, and you also make sure that the load connected to each phase are same or close to same. You cannot make it same because it's hard for you, because you don't know who all are switching the power, and then taking the power, right? So these 2 things are the main reason. So when will it happen? In which type of electric connections it will happen more? In the power distribution network, there the load aggregated values are going to be different in each phase, and there will be 2-phase, 3-phase, 1-phase connection, and then it's hard to transpose the lines too. So most of these, because of that, we say electric distribution system is unbalanced in nature. Electric transmission system is not balanced. That's because of the nature that we are representing in the system. So if you wanted to run an electric distribution model, you have to take care of the unbalanced nature. And if you are doing in an electric distribution system modeling to take care of unbalanced nature, you need symmetrical components, or you need positive sequence, negative sequence, and zero sequence represent. So how do you represent that in transmission system? Do you care about positive and negative and zero sequence? Normal operating condition? Do you care about that? No, you don't care about that. So how do you represent the electric transmission system? Well, you take one phase power, multiply it by 3, whatever the total, represent that as like a one line, and then you run the models and electrics. Good. So, you are just basically talking about this, and you also need to develop models in two other forms, which will come later. One is when the system is not in steady state, when the system is changing, not abnormal, changing. That type of study or analysis is called dynamic study or dynamic analysis. Okay, when will that analysis happen? It will happen when the load that is connected to the system is not just a noise, it is going up and down. Okay, so you treat that by changing the load in the form of what we call steps. Okay, when you change the load in the form of steps, you will see the generation will also change. So you see dynamics. Okay, not in cruise control. When the speed goes very low and you accelerate or decelerate, you see this, that is called dynamics. Okay, so you have to do dynamic study for representing. Oh, if you do a dynamic study, what type of models do you need? Dynamic study will change the power flow with respect to time. Dynamics, it changes the power flow with respect to time because the changing the load. So such model should be time-dependent models. What is a general classical time-dependent model representation? Time-dependent model representation in mathematics, you utilize a tool called differential equations or differential equation based models. Oh, so can you just run the models in differential equation using a differential equation of electric grid? You also need to run some of the devices which is not changing when the dynamics happens. How do you run the models? You run the models in algebraic equation form, right? Algebraic. Oh, by the way, I missed the little bit of connection. I'm just trying to storyboard as much as I can. Then I think I can quickly move because of this wide variety of all the models in the power flow you run through with respect to time or no time. Steady state models you run through no time. Okay, so they are called algebraic models. Algebraic model means that it is not nonlinear. No, algebraic models can be nonlinear. So two different things. Nonlinear and non-nonlinear. Algebraic and different, they are two different things. We're following this story, right? So algebraic models you have. So some of the devices in the system are dynamic, some of these are not dynamic. So how do you combine together? So electric grid is then represented as or so-called differential algebraic equations or DAE. You will see this term, people talking about differential algebraic equation, different algebraic, right? Some people also call this ADE, algebraic differential equation. I just flip it because you don't know whether algebra comes first or differential equation comes first because it's combined in closed loop form. That is the one which you do when you run a dynamic model. What happens if you are going to have a condition where something happens to the electric grid? Means a tree fall on the power line. Such condition when it happens on the electric grid, we call it the electric grid is operating not normal. Okay, so such things are classified as abnormal operation of electric grid. What happens if it is an abnormal operation of electric grid? You study the electric grid for abnormal conditions. One abnormal condition that you applied to study the electric grid is connecting one phase on a power line to the other phase on the power line, and you call that as fault analysis or fault conditions. Oh, can you connect one phase to the power line to the other two phases on the power line? Yes, you can. This is also called fault analysis. What happens if one phase on the power line connected to the ground on the ground? Yes, it is also called fault. There are 7 different varieties of fault analysis that you can perform on electric grid. And the hardest one, we call it all the phases connected to the ground, and that's called 3-phase bolted fault. And the fault on the power line can also be on line. Can the fault connect on the bus? You know node and bus now. You cannot say no, you don't know node and bus. Can the fault happen on the bus? Yes. Will the fault happens on the bus is worse than fault happens on the line? Yes. Why? Because all the devices are connected to the bus. Devices are not hanging from the line. Lines are just in the conductor that going from point A to point B. So because devices are connected on the ground, everything is affected very bad, and all the interconnections happens on specifically on the bus. So we call it three-phase voltage bus fault. Lot of words, but that is what the bad fault. So you study what we call a fault analysis. It's also called short circuit analysis, short circuit study analysis. Why? Why fault analysis is fault based on the real? Why it's called short circuit study, short circuit analysis? Because that affects the capability of the devices to supply the current towards this fault, and that affects what we call as momentary supply of current towards a fault, and it is tested using our short circuit study. Remember the short circuit study which we did? That's why we call. So short circuit study is for what? For the device. Fault analysis is for the what? For the system. But you interchangeably utilize because you really don't care about what you do. You just need to only worry about what happens on the system. But they are two different things, by the way. You just don't mention that. You say, okay, short circuit study. It's a study that you perform because your study is done on a device, on what happens to each individual device. Analysis, fault, use on the system. You analyze the system, what happens on the system. So you see, always you call it fault analysis. You don't call fault study. I'm saying all these things because there are a lot of things, especially on learners and researchers, many things that it seems that they don't really clearly see the difference. So we call it fault analysis. We learners say fault study, but you say short circuit study. Study is for a device. You are understanding the performance of the device or parts in the system, how it works. Analysis is for basically to understand on the system what happens on the device. This is giving you a few things. Hope you are understanding what I'm talking over there. It's good. Okay. So, so that's basically right. Now what? So let's look at the inverter out from the equation. Don't worry about the inverter. Okay, it's just an electric grid. Why do I want to model an electric grid without an inverter differently, hoping that inverter will come? My point is, let's assume that inverter is not in the electric grid. You're not modeling inverter as a device in electric grid, and you have an electric grid. Okay, an electric grid modeling, power flow study, you're already doing classically for how many years now? 120, 130 years or something, when the machine started, Stanley and these folks in 19, something like that. So, having said that, power flow studies have been done before, right? What is the new in power flow study when IBR comes in place? Without modeling an IBR, is there anything different? If there is nothing different, then I can say, hey, the only change is IBR coming. Let's model the IBR, connect it to the device, and then go for, right? Yes, there is one big difference. One big difference is that the power flow study, when you study on an electric grid, you study the power flow on transmission systems and distribution systems separately. And distribution system, you probably don't do a power flow study because you connect all the distribution load lumped on an electric transmission network and connect to electric transmission network bus as what we call it as a spot load. Spot load meaning one load. What's the difference between varying load and spot load? Is the number in the load changes, it's become non-spot? No, spot is on location, varying is on number, right? Spot loads are loads that is connected to one location. So when the buses change, different buses, you have different spot load. Do you have a buses without any load connected? Yes. You have electric grid with a buses without any load connected. So all the loads no need to connect it in all the buses. You connect all the loads in different buses and you represent this load and these buses as aggregated one load. Okay. What happens on the bus? Is that load connected on the bus and transmission network? No. The whole distribution system is connected on that transmission network. Do you care about distribution network? No. We just say spot load, one load. How do you represent that load on the transmission network? You represent the load as active power and reactive power. and you represent the load as S. S as in Sam. S is what? Apparent power. You represent the load as an apparent power, which is active and reactive power. And you put that number, one number, for the entire electric distribution. Is that good? Entire electric distribution, you put it one number. Yes, that's what we have been doing for 170 years. Will that work? Yes. Believe it or not, it works. And it works to run the power flow on transmission system. Okay. How about the distribution network? Yes, don't carry about power flow. You do a small way of representing the power flow on a distribution network to calculate the losses so that you want to know the voltage. So in the distribution network, the focus is to maintain the voltage profile throughout. The transmission network is focused on getting the power and connected as a spot load. Are you following? Is it getting complicated? You understand what I'm saying so far? Okay. So that's what you do. Transmission network power flow. Sometimes there is a distribution network power flow. You connect it with one substation and then connect it to distribution network. So do you need to think differently now when the IBR comes in place? Yes, you need to think differently. Why? Because the IBR, when it comes in place, there are few things that happens. Number one, these IBRs are connected on distribution system. It's spread out, and that is called DER, distributed energy resource. They are connected on this. What happens if they are connected on this? All the current flowing through this transformer and all the way right here, they are going to change. If these IBRs are pushing power to the electric grid, for example, electric vehicles, at some point of time, or taking power from the electric grid, so these loads are now coming to become what? Generators or load. If it is consuming power, it is called consumer. And if it is whoever is consuming power is called consumer. That is for probably market. If it is delivering power, it is called prosumer. Delivering power is called generator. And then if you consumer and prosumer both done in different time, consumer and generation both done in different time, it is called prosumer. There's a new producer and consumer, basically. That's the word people talk about in general when you go to the big group called prosumers. So there are folks who can act as a prosumer in this case. What happens if there is a rooftop solar panel on our building and it is supplying the power to the electric grid? What happens to that? It produces. What happens if this is consuming power at some point of time as a load? It is called consumer. So this whole thing becomes two main difference. One main difference is it's not acting as a generator, it's not acting as a load, it's also acting as a generator. Number one. Number two, there are multiple of such generators and load connected in different points. So the concept of treating them as a spot load at some point and putting that power at point and running the power flow will no longer work because these folks are seeing. What happens in the transmission network? Well, you still have distributed resource in transmission network. So you may not have to look at that way, and you may have to look at differently. So such modeling has to be done not just power flow models on transmission network, but power flow models of transmission and the distribution network together, and that is called integrated transmission distribution network and integrated transmission distribution network modeling, and it is also called integrated electric grid modeling. So when we look at the title of our GIAN course, IBR integrated electric grid modeling, it can be IBR integrated or it can be electric grid integrated because you have transmission systems and distribution. You see now, so that integrated word is a integration of studies on electric grids or integration of IBR on electric grids. There are two different type of part that we are trying to study. So today our goal is actually by end of the day today, hopefully to talk about electric grid, not conveniently bringing IBR in the picture model wise, and also not talking about dynamics or fault conditions, electric grid modeling in steady state, because we learned so far that we have a job to do. What is the job that we have to do? To develop power flow models of the electric grid connecting transmission and the distribution network. So having said that, how many minutes we have now? 30 minutes maybe? half an hour. Well, there can be conditions in which you have load on your house and you have solar farms. So when you, well, I want to also look at the concept of electric grid when you have prosumer connected. Prosumer, everybody know the word now, right? Prosumer. When the prosumer is connected, how do you model an electric grid load? It should be spot load, right? Now that spot load is not going to be spot load. So how do you model an electric grid when you look at from electric grid standpoint? Whether it is prosumer or consumer or whatever it does over there, I don't care what you do. I need to model. How do I model? I call that load as net load. Okay, what is a net load means? You're taking some power or you're giving me some power. Difference of those two power, I call it a net load. When I run the net load on one specific condition, is it net load changing with respect to time? Is a power from sunlight delivered to the electric grid? Assuming these homes are connected to electric grid, finding it. I think you know net metering and everything, like the PV farms connected to electric grid, delivering power to electric grid, then you get some money. When the PV farms are connected to the electric grid, you don't turn on the electric grid and you lose some money, right? So this is the net load, which means generation minus load. What happens if the generation is less than the load? It is net load. If the generation is greater than the load, it is net power coming from the generator, right? So if you are at a home and if you are having a rooftop PV and you are taking power from rooftop, still you have a load connected. So you consider this as net load and you model that as a net load and you still is a load. So when the load is higher than the generation, it's considered as load. When the load is lower than generation, it will be a generator. I think that's what your question is, right? There is nothing to do with the PV. Photovoltaics are still going to generate power, whatever it is, because of the load connected on electric grid. So having said that, I hope you got this whole story here. So this is an electric grid with a current transmission and distribution system model. This is the transmission system. This is the distribution system. What will you have to do now? Okay. Now I'll speak less and then ask you to engage more. So you understand what is happening on the slide. So the random, so will this model affect the randomness of the photovoltaics? Right? So do I have to run the spot load in different conditions? You should engage, okay? You should understand whatever you understood, you should take it. And then you should engage. Okay. Spot load has to be changing different. Yes, you need to, right? That's a different thing. That's called randomness, right? So the randomness transmission distribution system connected together is called co-simulation. Combine the simulations models of transmission and distribution system. Okay. All right. So now we will start looking at some basics. Is this story known to you? Can you read the slide and then say whether that makes sense to you? Transmission system, power producer has generating station, prime movers, transformer, transmission company, this distribution utility. Simple, right? Baseline. Okay. High voltage network, medium voltage network, loads. How do you manage the electric grid? You manage the electric grid in a control center, right? There are two levels of control center. One is called load dispatch center. I think it's called in here, which is basically dispatching the load based on whatever the load. What is dispatching means? What is dispatchability means? That's a big word, another big word. What is dispatching? Dispatchability means? What is dispatch?
Dispatchability probably has to do with ability to ignore the rest as per the
Dispatchability is spot on. Dispatchability means you ask me 5 megawatt, I'll give you 5 megawatt. You change, sorry, 7. Yeah, I'll give you 7. Say, no, not 7, 3. Yeah, I'll give you 3. You ask me 250,000, I'll say, no, my capacity is too much. I am too low, I cannot give you 2. Until my capacity, I will not bother you what you ask, I will give it to you. Okay, such resources are called dispatchable resources. Such To do that, you need two things. You need to have sources that can give that power. You also need what? You need a control system to change that source to give the power in combinatorial time, we call it, which means in a good time. Don't give the power tomorrow, give it sometime in near future, and we call that as dispatch centers, where it is controlling those power to go to the all the conventional generating resources are called dispatchable. How about renewables, inverter-based resources? They are generally called non-dispatch. You ask for 5 megawatt and I say, no, I don't have a sunlight. I'll give you Zoom. That's called non-dispatch. Can you make a non-dispatchable source dispatchable? You could, by some ways. That is what we call it as people are working on. So, for example, I connect a battery to this source. And I have a lot of money and I connect a big size battery. I store all the power in here and it's ready. You ask me 3? I'll give you 3. First is such called dispatchable. Oh, do you need a control system for that? Yes. So you take a base, you got to write it down. There are some things. One is the power requirement from the generating source. What is another requirement? Control system to do that job, to give the power. Okay? So people are working on dispatchability or dispatchable nature of IBR, how to make the IBR dispatchable. Or do I need to consider the dynamics of inverters? Yes, I need to consider who do you control when I want to make this dispatchable? Inverter, so do I need to know the control system of inverter? Yes. Is that going to be different from generator? Yes. So how do I need to control? Nice story. Everything you can do and do a 4 or 5 dissertation or thesis out of it, and then you can do research. And so I'm just giving you the context. So you know your scope in here, which is control system that is required. So system analysis and practical power system is done through this path, and for that you need to model of the system. Jumping onto models of the system, this is how you model a generator. If everybody is good, I will move forward fast. How do you model a generator? You model a generator as a source and a connecting inductance, because generator has an inductance, a generator generates a source, never EMF. Okay, so such models are generally represented in the form of 2 forms from electric circuits. All these models are background is electric circuit. I forgot to ask you how many of you got a first course on electric circuit. I hope you have done AC circuit analysis, which is important. Oh, is that DC circuit not important? Yes, it is important because of inverter, but that's not that important for electric system level study. So, what type of model that you are talking about for generating sources? We do that in 2 forms. What is called Thevenin model. Another is Norton representation. Thevenin models are generally called, in the power electronics world, and I'll tell you some analogy while I go through. In the power electronics, we call it as voltage source models. Okay, voltage source representation or voltage source model. Okay, is that voltage source same as voltage control? No, they are not same as voltage control. Voltage control means what you are controlling. Controlling is voltage. That's voltage control. So power system folks says that Thevenin model, power electronics source is a voltage source model. And that what's the difference between a Thevenin model and a voltage source model? There is a difference. Voltage source model is a model of that source directly at the source point. Thevenin model is a source representation not just on the source point. It may be somewhere else on the point. Still I represent as a source. Why do I do that as Thevenin model? Because in electric grid, if you wanted to reduce the size of the electric grid, some part of the electric grid I need to ignore. So another part of the electric grid, I stand here, I say, bring the source here, and then I call this as a Thevenin model, and I do that for. That's the difference. That's why we do Thevenin model. I don't know whether you're catching. I'm going a little faster now because I also have a content delivery time. So I hope it's okay. And I think somebody, whoever catches, can translate it also. So Thevenin model representation is done by voltage source connected in series with the impedance, generally called Thevenin impedance. But for a synchronous generator, it's not represented as Thevenin impedance. It is called inductance. Thevenin inductance. There is no resistance. Why? Generating sources in generators are necessarily represented as inductance. And this inductance is called synchronous reactance. In general, it's also called X sub S, synchronous reactance. X represents the reactance and L represents the inductance. What's the difference between the inductance and reactance? The fundamental frequency reactance is equal to 2 pi FL. So L is the inductance and the reactance. And why do you worry about fundamental frequency? Why did I say fundamental frequency? Which is 60 Hertz, obviously 2 pi F is. What happens if it is non-fundamental frequency? It is not going to be same reactance. It will be different reactance. Why do I say fundamental frequency? Because in steady state operating condition, we are running in fundamental frequency. What happens if it's a fault? Well, then it's going to be non-fundamental reactance. How do you represent a non-fundamental reactance of a synchronous generator? You call it XD prime. I don't know whether you heard of this term. We call it transient reactance. Now, what happens if the time will become so fast and the reactance value changes non-fundamental? Yes, then it's called XD double prime. We call it. I don't know whether you know these stories or not. That is a transition from the fundamental one moving on to XD double prime. So the representation of that in the form of X sub S. What's the next D? You're coming back again to what we call it as transformation from real to virtual. Real systems are A, B, and C, three-phase. If you represent a three-phase of a synchronous generator, you have to represent everything in three-phase. And we call that, oh, these three phases are balanced. Why do I need to spend a lot of time representing three-phase? So you bring the three-phase into two-phase representation and model. Magically, you can do that with the help of somebody named Park and Clark, who did a Park transformation and Clark transformation. None of the things is done by you. You are sleeping, you borrow what they did, and then you say that is transformed to ABC to DQ. Going through alpha beta, ABC to alpha beta, then go to DQ. How do you go to ABC to alpha beta and then to DQ? Story you can look at your books and then say. So you get what we call it as DQ. And that X sub S now will become X sub D because you care less about Q. The D is represented as active power related. XQ is represented as reactive power related. Why do you don't care about reactive power here? Why you don't care about voltage and reactive power here? Because you are doing steady state modeling and you're doing power flow. What power flow you're working on? What power? Active power. You're not working on reactive power. So, anything else in here? Okay. So, the represented is E. What's the difference between E and V? E is generally called EMF. V is generally called voltage on the bus. So, can E be V? Most likely no, because it goes through a EMF connected to inductor connected to V. Can V be E? No, because again it is connected to the source. Alright, so maybe there are other small things here. I may not have time, but pay attention to the details in here. This is how we model a transformer. Transformer models are known to you. Two-winding transformer equivalent circuit model known to you. Yes, everybody knows about this. I don't think, there is no brain here, and you represent it in the form of referring to primary, referring to secondary. All these are fundamentals. And at the end of the day, you neglect this. Oh, this is what it happens to circulate no load current, and we call it no load losses. This will not, only for full load test, you do not short circuit test, all the story. Now, if you neglect this, what happens to the transformer? Another series impedance. Generator is an impedance, the transformer is an impedance. What happens to the transmission lines? Again, an impedance connected. Okay? Loads. Loads are generally considered as the constant power loads connected to a point, and that's called spot load. There are two different variances of the load in real system. Real system loads are not generally. Do you know zip loads? Constant power, constant current, constant impedance. No? How many of you know zip load? Raise your hands. One. Loads connected to the electric grid. If I ask for 5 megawatt load, if I take 5 megawatt all the time, it's called constant power. Constantly taking 5 megawatt. So you may ask a question, will it take less megawatt. Yes, it takes less megawatt depending upon what voltage level you have. Taking 5 megawatt or electric bulb says that I'll take 60 watts. When 230, right? Whatever voltage is there, not 120, 220. So it takes 60 watts from 220 volt. What happens if the 220 volt become 120? Have you seen an electric incandescent lamp? Forget about this one. The one bulb. What happens to this bulb when you apply 120 instead of 220? It will be same as your candle, whatever it says on the reading, right? You know that, or you know that? So it is not taking that power. It is taking less power when the voltage changes. So they are not considered constant power. It has to take constant power all the time, right? So the loads are not necessarily constant power. So you may think, oh, then that means there are some loads which are changing with voltage. Yes, there are some loads which are changing with voltage. Such loads which are changing with the voltage can be categorized into two forms. One is constant impedance and constant current. Okay. What happens with the constant current? It keeps the current constant. When the voltage goes, power also will change depending upon that, keeping the current constant. What happens with the constant impedance? And when voltage changes, it keeps the current also changing to make the impedance constant. We call constant impedance. So there are three types of classifications of the load in the real life. How do you know that this is constant power and this is constant? I think you should do an undergraduate project. There is nothing like constant power and constant current. Then loads that is connected is a mix of constant current, constant power. So you want to represent the load in the form of a model to look at the system. Right? I'll tell you that model later. Now I'll go a little bit more detail about the electric distribution system. You understand the modeling of electric transmission system. This is fundamental. Now renewable energy IBR. Electric distribution system starts from a point where the electric substation is connected. If you do an electric distribution system study, what will you do in this point where the substation is connected? You represent that point as a voltage source. Connect a voltage source at that point. Okay. What happens behind the substation where the power is coming from the transmission system? What will you do? Just neglect it and connect there as a voltage source. So what's the property of the voltage source? You know, right? No, you don't know. What's the property of the voltage source? It will give you, no matter whatever current is pulled by this voltage source, it will give you, you say that the voltage at that point is stable. This voltage at that point is not changing. Yeah. So if you have a voltage source, and if this voltage source ideally is connected to another line and behind the scene, if I represent this as a voltage source, do I need to model anything behind the voltage source? You don't have. So you can cut there, say my life starts from there. So distribution network is modeling the substation as a voltage source. What happens to the voltage on the substation? Will it be constant? Then only you can represent as a voltage source. Remember? Yes, it will be constant. Who will do that? Somebody else will do that. I don't care about that, and I will do as a voltage source. So this is how you. So if you have anything to be modeled, if you cannot consider that as a voltage source, please don't consider it as a voltage source. That's what I'm saying. So it's important to know what you are trying to do in your modeling world. So voltage source connected to what? In the beginning of life, in electric distribution system, it goes to a transformer first. And that transformer is generally known as LTC. Not the same name, I guess. It's OLTC. OLTC is LTC is a short form, and OLTC you can call it as long. What is OLTC? On load tap changer. Have you heard of this? What is on load tap changers? Changer means it changes the tap of a transformer. Do you know the tapping transformers? You know what a tap of a transformer means? I only target you, undergrad. No worry about other. Do you know what a tap changer transformer means? How the transformer works? You know, transformer changes the output voltage based on the input voltage, and that is done through stepping. It's called stepping up or stepping down. What is a tap changing transformer means? What is a non-tap changing transformer means? It step up and step down, only one voltage. 220 volt, 12.47 kV. If I ask, can I get 7.47 kV? It will say, no. I am designed for stepping up 12. What's the tap transformer means? Tap means up to 12.47, I can tap and then get any other voltage in between. Called tap transformer. I'm just very baseline saying, otherwise there is a knowledge gap. So tap transformer is used to what? Tap the voltage, change the voltage. Why do I need to change the voltage? When the current flowing on the line, distribution line changes, is that current flowing on the distribution line in your control as a utility or as a generator? No. Who will change the current flowing on a distribution line? The houses, the loads. People like, I need light and I change the current. When the current changes on the distribution line, what happens to the voltage? Voltage goes up and down. Why? Because of the drop on the distribution line. This is fundamental. So when voltage goes up and down, who will have to maintain? Oh, do I have to maintain that voltage? He said constant voltage, right? I mean, who will maintain the voltage? Utility has to maintain the voltage. If the voltage is going down, utility will shift the voltage up. Utility will change. So there is a device in the electric distribution system which does the job at on the substation side, and the name of the device is OLTC. It will look at the load and then change the voltage. That's why it's called load tap changer. If that is done online without somebody going there, changes. Done online, it is called on-load tap changer. Oh, is there an off-load? Yes, there is an off-load tap changer too. But it's done. These are something in general control theory wise in electric distribution system, we call it tertiary control. Tertiary control means it's going to take some time. Can this happen in every second? It happens in 5 minutes, 15 minutes, 20 minutes. There it happens in 15 minutes interval, or one time in a day, or one time in 3 months. This is what generally happens. So it actually changes with the load connected. Following, right? So how is the voltage changed? Dependent upon voltage or current? Depend on current. Said load. Oh, so you may ask the question, oh, is there anything else which changes based on voltage? Yes, there is somebody else. One thing is there in India, that's why I gather from IISc. That's somebody else who changes the voltage based on voltage. So if you keep a transformer, and I look at my, do you know in a transformer something called load side and source side? Source side is a source connected to the load side is a load that's going in. If I am a transformer, I look at the load side and there is something voltage changing on the load side. I change my voltage on the source side. Such transformers are also tap transformer, but they are operating based on voltage on the source side, changing the voltage on the load side, changing the voltage on the source side. Why do I need that? If I do that, if I yeah, it is not required, but I will go back again. So if you look at a distribution network, we have a long line connected distribution network. There are buses in here. Distribution networks are generally considered as like a tree formation. This is how a distribution network looks like. Okay, this is like a tree. You see a tree? How many of you see a tree in my drawing? It's a tree. This tree has a main trunk here, and there are branches. Okay, in the distribution network, these branches are generally called laterals. Laterals means branches. Okay, this trunk is always going to be mostly 3-phase. Okay, we have 3 trunk which is going out. These laterals can be 2-phase or 3-phase depending upon the connection point, and from here it can be 1-phase or something like that portion here. This is how you represent a distribution network in general. So will you see unbalance on the distribution network? Yes or no? Why? No, no. Lines are 3, 2, and 1. Oh, how many unbalanced I can have? Yes, load is that also important. How many unbalanced I can have? Two type of unbalance we talked about. Remember? One unbalance is because of change in the load, single phase, three phase, two phase. What is the other type of unbalance? Lines, bringing unbalance. It can be. Can you have both in distribution network? Load unbalance and line unbalance? Yes, you can have both in them. It's a different story. I'm digressing a little bit, but I'm just connecting with this what we discussed. So this is a distribution network. Okay. What happens for the voltage in a distribution network? If you plot the voltage on a distribution network, starting from substation, looking at these buses points, depending upon the distance, you will see the voltage on the distribution network mostly something like this, which means that you have 1 per unit here. You may have 0.95 per unit at the last point. This is with respect to distance, and these are node numbers. I'm plotting the voltage at every node. Okay, node numbers organized in the form of the distance, not necessarily node numbers starting from the substation. Why am I saying that distance again? This one point right here, this distance is more. I'll be putting this distance and up to this node, then I'll start from this node because that distance. Okay, so when you have like that, this is the voltage. If it goes from 1 to 0.95 at this point, you're good. I'm happy. Everything is taken care of. What happens if this one goes like this, 0.92? I have a problem. The loads connected from this point to this point, they will see under voltage. When you see under voltage, the loads which are connected, lights will not turn on. We talk about incandescent. So there is a need for me to boost this, right? Can I also change this line? This line like this. So I shift this entire line. Okay. So if I shift this entire line, how do I erase it? But if I shift this line, let me say I'll do this differently. I got it. So I'm moving this line now. Up. If I move this line up from here to here, will it work? Yeah, it works. What happens to this voltage? Well, I have to make sure that this voltage will not go beyond 1.05. Right? You understand per unit? Everybody understand per unit? 0.95, 1.0. Okay. So if I can lift this and I bring this to 0.97, everything is good. Who does that? This is done with the help of LTC. So what is LTC doing? LTC is looking at the load and then shifting this up. What happens? I shifted this up and this voltage become 1.1. I will shift this down. Let's say this is 0.92. And I shift this down 5 points below to 1.05. And I shift this down 5 points below, 0.97 will become 0.92. So I have a problem. I cannot shift it up, I cannot shift it down. What will I do? You see the problem or you don't see the? How many of you see the problem? If I shift it up, it's hit more than 1. If I shift it down, it's going below 1.95. Can that happen? Yes. People are not looking at it. I could see what's what. Do you see? Okay, what will you do? Oh, I have another trick. I'm going to keep it right here and I'm going to boost. I'm going to redraw this. 0.95, 1.05. It's bad news, right? At this point. So I will do something to move this up and then do this. Again, my drawing is not that great, but move it. Can I do that? So I go from here to this point, then I shifted this voltage up, then as long as I shift it between the band here and then bring it here, I'm good. Are you seeing this? To do that, what do I need? I need somebody here sitting and shifting this up. That job may be suppose here. Who will do that job? This is done by somebody called voltage regulator. What's the difference between voltage regulator and LTC? Voltage regulator will look at the voltage and regulate the voltage. What voltage? Voltage at the load end of a transformer. Regulate the source end of the transformer. What happens to the LTC? It looks at the load and changes the. So this voltage regulator is a device also used to regulate the voltage on electric distribution system. So so you represent that in the bus variable mode, and then it'll take 5 minutes more. Is that one?
Yes, correction. The difference between the voltage regulator and the LDC cannot be very clear. Ultimately, both are doing
the same thing. Both are tap changing. One is changing the tap based on the load side voltage and changing the tap on the source side to improve the load side voltage. Another is changing the tap looking at the current on the distribution line and changing the tap to improve the voltage to change the tap. Again, load side. But one is looking at the current, another is looking at the voltage. Okay. Yeah, it's just the control method is basically what is doing the trick. And the essence is the same. So do the current and change the voltage. What will the controller do? Controller is doing the I times Z, changing the I times Z to change the voltage and change the tap. The other one is doing the voltage on the transformer on the load side and then changing the. So the one who does the voltage and changing the voltage is called voltage regulator. On the distribution side is called distribution voltage regulator, DVR, distribution voltage regulator, not distributor, distribution voltage regulator. And the one who does on the changing the current and then looking at the current and changing the voltage is called load tap changer, looking at the load. And so you may ask, there is a little bit story behind it. I haven't completed the whole story, which was not the whole point. So you may ask the question, looking at the current and changing the tap of the voltage, right? It was beyond the time, but.
Sir, can we go for voltage upliftment by using the FACTS controllers?
Yes. So that is a good story that segue to few things. Can I control? So this is a load tap change. I mean, this is the voltage regulator doing the job, right? Voltage regulator doing the job, right? What happens if I connect an inverter there? Can I change the voltage using an inverter? Yes, you can. Not necessarily change the voltage, but you can change the reactive power coming out from the inverter. If you change the reactive power coming out of the inverter, will the voltage change? Yes, voltage can change. So can I use an inverter to change the voltage instead of a tap changer? I mean, instead of a voltage regulator? Yes. Will that be beneficial? Yes. So we there is a project we implemented in the field. We said that the regulators, some regulators are not even required if you have a inverter connected at that. So we call it in our thing called asset release, meaning you invest 2 million. So one regulator is generally costing 800,000 US dollar. I mean, just a general number. I don't know the number here. But that regulator, you can take it out, put it somewhere else. That's called asset release. So you compensate for the investment. So you have a big inverter sitting there. The inverter money is kind of offsetted because of that. So there are many things. So can a fact device, you can put it to regulator? Well, yes, you can. Is that fact device putting there is an overkill? If you have an inverter connected at that point, overkill means, is that really required? Is the inverter connected and you also get photovoltaics coming out? Maybe that's the best option. But the bottom line is that voltages needs to be controlled. Now, these voltages are generally controlled in every 15 minutes. This is normally done in 70 seconds, something like that, the time frame. This is 1 minute, 1.5 minutes. So anybody who can do that job less than 70 seconds, can you control? What I mean, if there is a device does the job 75 minutes, I cannot use because this is running. So time frame is important. It's done by all control systems, done by the controllers working on the device, not necessarily functionality of the device. Controllers on different devices are differently. Fastest one are power electronics based devices, which you can perform very fast and get the controller done. Is that a fast? Too fast is a problem? Yes, too fast is also a problem. So how do you regulate to make it, so these are all what do we call it, devil in details kind of thing. A lot of things needs to be assessed carefully. But is that a good thing to do a study? Yes. So just to say some juice for thought for this. Yes. So fact devices can also so everything can be modeled. So how do you model a line? How do you model a load? This is a load model. This is a zip load model. Zip load is actually represented as a constant current and constant impedance. This coefficient on the top, you can change to give you a combination. You can change to square, which will give you voltage square, basically the power representation. You can change to 1.05. That means it's a mix of constant power and constant current type of. So there is these are all classical, meaning this is in the books. This is in the literature or whatever you call it. So it's nothing new. I'm not bringing something, but since it is a course, I'm, talking about the old, what has been done. So this is a zip representation. This is a constant power, constant current, constant impedance. This is a representation of a voltage regulator, input and output. So you can control both based on VJ controlled based on VI. VI is generally called that I is generally represented as input voltage and that J is represented as an output. And A is what we call it as tap ratio. I don't know whether you've heard of this term. Tap ratio. How do you model a tap ratio? What is a tap ratio? What is it?
Percentage of the
Voltage output divided by voltage input nominal is basically what we call it a tap ratio. Tap ratio is number of turns on the secondary, number of turns on the primary divided by number of turns on the secondary. N1 divided by N2 is V1 divided by V2 is called as A. This is third year, second year. So I think you should also know, but that's what the tap ratio is. So we have that. And this is how we model a capacitor, and you can also model an inverter. This is a first inverter model representation. Very simple. What is that inverter doing? Inverter is looking at the rated power and subtracting that with the power flowing from through the inverter. Why do you subtract the power flowing through the inverter? Because that's the requirement for the photovoltaic. I will say that, hey, I need to get 5 MVA or whatever. Subtract the 5 megawatt. You subtract the power flowing through the inverter. Then find out how much reactive power is left in the inverter based on the capacity. And you use that reactive power to what? To regulate the voltage. Such inverters are called smart inverters. Many inverters do not have that capability. Do not have the capability means what? Is this reactive power? Oh, it's a story, another story. Where is this reactive power coming from the inverter? Is that because of the inductance? Oh, can the reactive power comes based on inductance? Can you get a reactive power based on inductance winding? Yes? Yes, okay. Can you get the reactive power based on a capacitor? How do you get reactive power from the inverter? Do you have an inductance inside the inverter? Inverter, not the filter. No. Do you have an capacitance inside the inverter? No. How do you get the reactive power? Reactive power of the inverter is free. It's coming without any cost assessed. How do you get it?
Change the phase of the current.
It is actually that we get it by the difference between the angle of the current and the voltage flowing through the waveforms inside the inverter. Oh, by the way, there's a fundamental difference in analyzing something inside the box, which is power electronics, and something on the electric grid. Electric grid, you analyze everything in, most of the time, in phasor representation, which means you represent in RMS quantity, phasor, and angle. Inside the inverter, when you go there, it's another world. You will see always waveforms. You will always see waveform. There is nothing which we call it as phasor. You always talk about, so the RMS value is not existent inside the inverter. You only talk about peak. You don't care about RMS because you don't worry about RMS. Angle, no. Only sine omega t plus theta or sine omega t. Everything is represented in the form of waveform. But because it represents the form of waveform, there is a phase of that waveform changes, you get reactive power. That's how you get reactive power. So it's a different way of control. Why? Because Q that is coming out is VI sine da da da. What happens in the electric grid? Q that is coming out is V square divided by Z minus U. So you got a Z or the X, which comes Z, by the way. We call it Z, and I changed my style Z, V divided V square. So equation is different, analysis is different. Just to give you. Okay, so power flow model, I don't think we'll have a lot of time, but we'll wrap it up and then we will come back, and in the afternoon we'll talk more about it. But I will just talk about the power flow. If you want to do, so in the afternoon session, we'll just go on power flow. We talk about power flow of a distribution network, power flow of transmission network, and integrated power flow of distribution transmission network. I will just give you a segue on how do you do a power flow. Power flow is done using these three main equations. That's it. Okay. So you take a bus. You say that the power going into the bus is the same as power going out from the bus. This is something coming from very famous fundamental called KCL, or Kirchhoff's current law. Current going in is the same as current going out. Which equation represent here? Current going is equal to current going out. Which equation represents that? This equation right here represents the power balance equation. What happens in the power balance equation? The power coming in, it is the same as the power going out. You can represent DR, load, everything on the power balance equation. What is the second equation that you see in a power flow? Second equation is voltage equation or voltage drop equation. We talk about the voltage on this bus related to voltage on another bus. How these voltages are related? Voltages are related based on voltage drop and reactive power drop. So this is basically the voltage balance equation or voltage drop equation that happens on the electric grid. One more fundamental equation which is coming out in all these things, you represent them in complex form or in apparent power form, which is S, which is represented as VI conjugate. Conjugate is another story. Why conjugate came there and all the story, probably you know that. So when we come back, we will do the power flow study or what was. Yeah, after break.
Sir, thank you very much for enlightening us with the modeling aspects of the inverter-based resources. And you have started the discussion with very fundamental part. And I hope that we all have learned a lot with this session. So thanks a lot, sir, for this particular session. Again, we will meet after the break, sharp at 2:45 p.m. here only. All right. So everybody is requested to proceed for their lunch and then again reassemble at 2:45 p.m. sharp. Thank you. Thank you very much.
Thank you. सबका वो right ये खोल करिए
Welcome back everyone. We now resume with lecture 2 on power flow of integrated power grid considering both transmission and distribution system of the day. Please join me in welcoming Professor Kamalasadan sir once again for another session of valuable insights.
Yes, I'll yeah, I'll take it. Okay, so what we will it's my God. So what we will do is we will start from where we left, and then we will move on. Better, better. So what we will do is we will start from here and move on to the next part. So just a recap, what we did so far was talking about how to model the electric power grid with the inverter-based resources under the knowledge of having inverter-based resources coming into electric power grid, how to model electric power grid. That's what we were talking about. And one big change as far as the modeling, and then modeling also, we were saying that modeling, we are going to talk about steady state modeling, right? Steady state means models are developed to study the power capacity, right? Analysis, power capacity analysis. So that type of model is generally used for what we call it power flow analysis, right? So that's what we were talking about. Power flow meaning evaluating how the load is connected to the system and how the system behaves when the loads are connected to the system. So from that context, we said one big change that happens on electric grid if you were to study the electric grid when the inverter-based resources are connected is to have the electric grid studied together as a one electric grid. So you may ask the question, well, is the electric grid studied differently before? For power flow, we used to study the electric grid as power flow transmission network and power flow for distribution network sparingly, right? Now, if you want to have the inverter-based resources connected to the electric grid, you must study the electric grid together of the power flow for transmission and the distribution network. So that was a premise. So what does that mean? It means that you need to run the power flow, you need to know the power flow, how it's been performed for transmission electric grid and the distribution electric grid, right? So now what is that study means? It means modeling of the devices and the devices connected electric grid. So what we did, we started looking at the models of electric grid for conventional electric grid. We started looking at the generator models, transformer models, load models, and that is for the transmission network, right? Then what we did? Then we started looking at the models of the electric grid, how that is represented for electric distribution system. Okay? So we looked into models of the electric grid, how is represented on electric distribution system. And in the electric distribution system, we said, well, it's unlike transmission system. You will look into what we call it as the substation connected to the distribution feeder. On the substation end, you will treat the substation as a voltage source, right? Substation as a voltage source. And then you have devices connected, and there are mainly two. So in the distribution network, your goal is to maintain the voltages on the distribution network properly, right? Why do you want to maintain the voltage properly on a distribution network? because there are a lot of loads connected on the distribution network, right? So the loads are connected, the voltage will start changing. So you are maintaining the voltage properly. So you look at what are the devices that actually does that job to maintain the voltage properly. And we identified two main type transformers that's connected on distribution network that does the job of maintaining the voltage properly. One transformer is called, both are tapped transformer. One is called LTC or OLTC, which taps the transformer to improve or decrease or increase of voltage, looking at the load. Looking at the load connected. That is called LTC. Looking at the load connected, which is a current, okay, of the load. Another type of transformer that is called tap transformer again, which is used to regulate the voltage, looking at the voltage on the load side and regulating the voltage on the source side. So there are two different. So the first one, looking at the current and regulating the voltage, is called LTC or load tap changer, OLTC. Looking at the voltage on the load side and then regulating the voltage on the source side is called voltage regulator, and it's also called distribution voltage regulator for on the distribution network. So we talked looking at both of them, and then you have devices such as capacitors connected to the points where the loads are connected. Capacitor also does the job of improving the voltage, right? Capacitor does the job of improving the voltage by changing having the capacitance value. There are two types of capacitors that is connected on distribution network. One is called, maybe you may not know, one is called fixed capacitor, where you take the capacitor bank or a can and then connect to the bus, which changes the voltage directly from capacitive reactance. So capacitor is not a device changing the reactive power. Capacitor is changing directly the voltage, changing based on capacitance connected to the network at that point. That type of capacitors are called fixed capacitor. There is another type of capacitors which is connected to the point to change the voltage, which are called, it's not variable, it's the same capacitor, but they're called switched capacitor. How does that work? It works based on switching in and switching out. So those capacitors are in or out. It's not varying or variable, but number or no number, right? That's like a switched capacitor. So switching of the capacitor can be done based on current or based on voltage switching or current switching. So that's basically the capacitor and the load. And then you have the distribution lines. Lines can be 3 lines, 2 lines, 1 line, depending upon how the distribution network is plotted. Okay, so that's where we were. Good, right? Makes sense. That's where we were, and then what we were started looking at was looking at the equations for the power. We looked at saying that the bus variables are actually the voltages. Oh, we also talked about bus and node. Everybody's okay with that, understand, right? Bus variable is the voltage and the branch variable is the line currents and branch power flow. So there are, when you look at the our distribution system especially, we have two quantity. One is called the bus or the node. Another is called the branch or the connected line. If you are talking about voltage, you always talk about the voltage on a bus, not voltage on a branch. You don't see any voltage. You have bus voltage connected to the ground point, right? Branches are actually reserved for flow. That's basically line current flowing through the branch or power flowing through the branch. We have bus voltages and branch currents. Branch current has, obviously, we said they are all in phasor representation, which means there is a magnitude and an angle, right? Remember, everybody in phasor representation, phasor means like a vector in a magnitude and angle. And then you have a power flow represented in the form of apparent power. So the apparent power includes the active and reactive power. Active power in the active power domain and the reactive power along with that. So they are phasor complex phasors, right? Phasor representation in the form of a complex quantity. Make sense? So So the state variables, when you look at it, are the voltages, and the branch variables are mainly the currents. And you can devise models. You just talked about the device model, how the models are developed for the device, and we also talked about how the models are developed for the VER and also the capacitor. Next, I think we discussed this. So good with the VER model. Okay, so then we said, well, if you are looking at a power flow model for a distribution network or for any system, there are two main equations for the power flow. First equation is called the power balance equation, where you want to write it down. These are the name of those equations. Power balance equation, where the power coming in is the same as power going out, is the power balance equation. And the second equation is basically voltage drop equation. So let's assume that you are looking at these 2 points. The voltage on Vj is equal to voltage on Vi. This is a mathematical representation. So I'm specifically talking about how do you write a math equation. Sometimes when you have a physical sense on how to do it, when you start doing a model or writing a paper, or writing a book, there is there's a language that you speak when you say something. And if that's not the truth, then people will not understand. So you have to really specifically say the way that is written in the math. So for example, if you're looking at Vj, you say Vi minus Zij. Zij is impedance of the network, and Iij, that's basically the voltage drop. And Sij is what? Is that a power, injected power on a bus, or a power on a line? Sij is what? Power flowing through that branch. You see, it's going through that branch, not the power on. Yeah. For power, when you talk about, there are two types of power. One type is power flowing, whatever is power flowing. Another type is power on a point, which is incoming minus outgoing. So you have to think about that. And then you have a power balance equation of Sij minus Zij, Iij, that's conjugate. That's basically I square. That's equal to Sjk plus Slj plus dr. So Sjk is basically the power flowing through from this branch to Jk, plus Slj is the power on that load on there, minus Sderj is a der on that one. Right? So what happens if there is no der connected here and no load connected here? What happens to these two variables? They're going to be 0. So what are these equations? These equations are generally called generic equations. Generic equations are equations. When you write after the equations are written, what you do is you develop an algorithm and then you write a software code, right, in MATLAB or some other script. So when you write a software code, you want to run that algorithm, you can write it in two different ways. One is to write it for a specific system, 3 equation, 2 equation, or you write it for a generic system. When you write it for a generic system, it's applicable for any bus or any node. So that's how you should write. So if you are looking at equation, you can develop that equation in a generic form or a specific form. When you write it in a specific form, you will be doing it for that specific case study example to understand whether you have written it right, or you are troubleshooting and you are evaluating. You make a generic form. Okay. So if you are having this equation, this is a generic equation we call it, because these two loads and the DR connected at this point are going to be 0 for this specific bus, and this Sij minus the drop right there is going to be your power. Are you following? 3 equations, or either 2 equations and 1 derivative, which is apparent power equation. Good? Okay. All right. So with that being said, that's how the load flow is run for a distribution system. Now the question is, why do you need a load flow for a power distribution system? I think we talked about it. I just wanted to reinforce one more time. Load flow for a distribution system is required for what? Okay, for a conventional system, no IBR, no integrated, it's conventional power field. Do you want to run a load flow for a distribution system? Yes or no? Or do you want to run a load flow for a transmission system? Okay. You want one for distribution system? Why do you want to run for load flow for transmission system? Yeah, you can get the difference between the source and, but no, yeah, so the just to see whether source is sufficient to okay, yeah, that's one objective. Source is sufficient to supply the load. What else? Why do you want to run a load flow? Angular displacement of what? One of the main objective for the load flow is to get the voltage magnitude and angle of an electric grid. So the next question, why do you care? Why do you want a voltage magnitude and angle? Oh, how do you get the voltage magnitude and angle? By connecting the load to a specific point in the model and running the load. When you're connecting the load to a specific point, you are finding out the voltage at point. So if that load is changing, will you get another voltage? Yes, sir. Yes. So for several loads, you can get the voltage, right? So why do you care about several voltage, several load at one load and one voltage? Why do you care about that? Why do you need that? You understand my question, right? Why do you need that? Why do you need to run the load flow? That's actually a fundamental question. Why do you need a load flow? What is the purpose of running a load flow or power flow? You're not sleepy, right? What is the purpose of running a power flow? Huh? Understand the performance of the system. What do you mean by performance? What do you understand? What is the voltage level? So why do you want to know what is the voltage level? Very good. Yes, understand the voltage level. And it's the same thing that we said that the power flow is run to get to the voltage magnitude angle. Why do you want that? So the reason for that is same thing as the water flowing through the pipe, right? You are trying to understand for a different load, what will be the voltage on my system? Is all the voltage good, right? Everything is excellent. If the voltage is not good, if there is a dip or higher, then what will you do? Okay, to understand that, you run the flow. Suppose the voltage is dropped or dip, what will you do? You can put a device on a specific location where the voltages are low or high to balance that voltage. For doing that, you need to know some tool. You need to have some tool to run. The main purpose of the power flow is basically that. Okay, it's actually done for the design, during design, suppose it's some or planning purpose or something. So planning purpose means what? You do the load flow again when the load is changing in future. Yes, you can do the load flow multiple times as a tool to understand what that voltage and magnitude is. So what we call it as the state variable for a load flow. When you run a load flow, is to know the voltage and angle of voltage. State variables in the load flow is basically now voltage and angle of voltage. So voltage is, understanding the voltage is very important. What is another? We also said that if the resources are not correct, I mean the generation is not there, obviously the load flow will diverge, we call it, or will not work, or not give you results. So that's another thing which you get. What is the other thing which you will get from load flow? So another important thing, as far as economic standpoint, for the electric grid, everything is great, voltage is great, power is given from the source to the load, but how much power we are losing in the transit by when you generate the power from the generating source going to the load, how much power we are losing? Why do you want to know that? How much power you are using is directly proportional to money, and you want to know whether you can save some power to not lose that power. Two reasons. One, obviously money. Second is obviously you will get to generate a lot, right? So the objective of that power flow is, main two objectives are voltage profile and the losses, not having enough generating sources. If you do not have enough generating sources, obviously it will not work. But fundamentally, these are the main two things that you will want to know for the power flow. So power flow is used for planning purposes, and some of the things are written here. Power flow is used for planning purposes, and power flow is used for long-term operational purpose, how much voltage profile you have, what different load condition, and so forth. Load flows are also important if you want to supply the power through renewables. If you want to connect the renewable in a specific point, what happens to the voltage at that point? Will the voltage be great if the renewable has more power coming in? If the renewable has less power coming, will the voltage going to go low if the power is not proper? These things are important for the power flow standpoint connected with the renewables. So it's important to know, both the renewables are connected. So that actually is what we call it as BER or renewable integration studies. Integration study meaning you're connecting renewable at some point. Oh, is that a connecting point of a renewable? Can you control the connecting point of the renewable? So a lot of thesis and dissertation you will see, it's called DER placement. Where do you place? Optimal location of DER placement. Optimal location of DG placement. Optimal in some other time, in 10 years ago, there used to be something called optimal location of PMU placement, some device placement. Optimal location of device placement is great to do a study as far as an understanding is concerned, but it's not very feasible because the PV where it is connected and which location needs to be connected, you cannot control or you cannot guide. It is based on policy, it's based on where the land is, it's based on what the government says, a lot of other factors. So optimal locations are generally, it's a great theoretical study, but not very feasible. But after you are designing the locations or finding out the location, what happens to the electric grid when the DER is connected? It's called DER integration study. Make sense? So analysis of impact on DER on existing system, you can do that as well. And what we generally call a smart grid study, which is, I think, it's a big word there. So I'll tell about that a little later. But, so that being said, we now understand the need for power flow and why do it with the power flow. So now what we're going to do is we'll dive a little bit into a little bit more on mathematics and try to understand how you develop these models of power flow. So power flow in general are done in electric transmission system and electric distribution network. In electric transmission system, power flow is done as one line, treating all the three phases or three lines as one line. Okay. So that is generally called as one phase analysis, right? One phase analysis. Most of the time, those one phase analysis instead of phase power flow in transmission system, it is done on positive sequence representation. Okay. Why no negative sequence? Because there is no unbalance generally represented in the transmission system, and no zero sequence. There is no unbalance represented in transmission system. So the transmission system models are generally called as positive sequence models. Those positive sequence models are used to run the power flow. What do you mean by positive sequence? Well, positive sequence is the same as all the phases power divided by all the phases power added together, or one phase power multiplied by 3. This is basically same as positive sequence. So if you convert from phase domain to sequence domain, and if the unbalance is not existing, positive sequence representation will be the same number as your phase representation. So you run in the positive sequence representation, so you don't have to do divided by 3, multiplied by 3, and then per unitizing, and then messing up with the number is not correct. All those things are avoided if you run in a positive sequence representation. So there is a group of power flow that runs on transmission system, mainly 3 of them running on transmission system, called 3 different ways of power flow. How many of you have heard these 3 names? First 3 on power flow. If you can raise your hands. I know you all are, but all of you. Can you raise first 3 names in this slide? First 3, these 3 names: Gauss zero power flow, Newton-Raphson power flow, fast decoupled power flow. How many have heard? You have heard these names, not done anything. Heard these names. A few people have not. How many of you have worked on these all three? Not developed code or anything, but have seen it, did some course around that, some level of knowledge for all the three. How many of you? Okay. So there is a knowledge gap, so I need to talk about transmission system. These are actually conventional systems. Right? Okay. How many of you have done at least one? So still there is knowledge gap. And which is Newton-Raphson? Causal and all right. So we have three different ways that you run a power flow and transmission system. One is called, can you read? Hospital power flow. Second one is called, okay. Third one is called so I'll, I think, take 10 minutes to just go through that. So the power flow models, is that power flow models algebraic or differential? Is power flow models made of differential equations or algebraic equations? How many of you think that power flow models are based on differential equations? Oh, nobody? Yeah. How many of you are thinking that power flow models are based on algebraic equations? How many of you are thinking that power flow models are based on neither algebraic equation nor differential equation? Well, two people raise hands in both of them, I guess. Okay, are you? Is there any? Is that question not clear? Do you know algebraic equations, right? Are these equations algebraic or differential? Oh, these are power flow equations, we said. I mean, some form of power flow equations, right? Are they algebraic or differential? 100% sure, algebraic? How do you know it's a differential equation? What are the characteristics of the differential equation? You have a time-dependent variable needs to be there in this. There is a time-dependent, no time-dependent variable. So they are not differential equations. They are algebraic equations. Are you thinking in your mind that confusing with nonlinear versus algebraic? Are they nonlinear or linear? Are these equations nonlinear or linear? How many of you think these equations are linear? There is no, by the way, I need all to raise hands, okay? No doubt. You be in one bucket or the other bucket. Don't stand in the, I cannot, then there is no problem in saying wrong answer. I don't think there is any penalty for wrong answer, and there's only penalty for attendance. 90% attendance is required. That's it. There is no other penalty or credit for a wrong answer. So please say something, whatever. How many of you think they are linear? Whatever you see on the board. There is nothing part linear, part non-linear, okay? All these equations has to be linear if it is a linear one. All these some of the equations has to be non-linear to become a non-linear. How many of you think they are linear? Okay, how do you know whether they are linear? Okay, let me ask. I think that could be a reason. That's why Vi, one variable here. Is that a linear variable or not? Oh, complex and linear are different. They are linear or huh? The linear, one variable. Another variable here, linear. Z, linear. I, linear. So is this equation linear or non-linear? So first one is linear. This one is not a linear, it says. This one is complex, but this one is not a linear. Is that linear or not linear? Linear? Non-linear. This equation is not linear, he says. Is that correct? Everybody agree? Why it is not linear? Hmm? Which one multiplied? V and I multiply together. And if you multiply V and I together, then it's not non-linear. I mean, it's not linear. The two variables, you multiply the two variables together, then it becomes non-linear. What is the property of non-linearity, by the way? Oh, maybe a little interesting question here. What's the property of non-linearity? If it's a non-linear, then you will see a variable that is square or cubic or some, they are non-linear. Right? If the variable that is not square or cubic, that can be considered linear, right? If the variable that is multiplied by sine function or cosine function or something, it is non-linear, right? So now let us look at these two. Are they square? Is V square? Can you see V square? I square. So, and are they sine, cosine? No. So, are they linear? I'm actually probing these questions because this is important for modeling purpose. Huh? They're sounding linear, right? But are they truly linear? Are they truly linear? You understand my question, right? Or yes? So react, whatever, react again. Okay, forget about that one. Look at this. Linear or non-linear? Non-linear. Or linear. Okay. So they are called power, right? See the power here. Oh, is this linear or non? Is this is this term has a square term? No. Is this has a square term? Has a square term? Yes. I times I. That's a square. Even though I don't say square, put two terms. Yeah, this is non-linear, so the whole thing has become non-linear. How about this now? It's a complex term. So if you try to treat that complex term in terms of rectangular or Cartesian coordinate, then you will inherit what we call it as a cosine and sine function. Then it will become truly non-linear. Let me not do that. I'm not going to write, okay, I write it in the form of a polar form. So there is no cosine and sine, angle and the magnitude. Will this become non-linear then? Could be not. So what are the criteria? The criteria for non-linearity is that you should not have the terms associated with that, right? So if you try to break that into separate equation, and you write two separate equations, then obviously you can treat it as linear equations. If you break it into, let's assume all these complex equations, we make it into two separate equations. Then they can be treated as linear. However, if they put it in Cartesian coordinate, still you can break it and put it in Cartesian or rectangular coordinate. Then it will become non-linear, right? So the other part is you see this VI conjugate, right? What is VI conjugate? Let's assume that you delete all the I and put V instead. So I equal to V divided by Z. So VI conjugate is V square divided by Z. Then it becomes non-linear, you see? Right? But if you keep the I there and no complex connected, two independent variables, if both independent variables are independent variables and not dependent to each other, then you can treat them as separately and then you can write that separately. Why am I saying all these things? This is a trick that you may have to do if you want to do what we use called as optimization methods, which I think we are going to talk about it tomorrow. And especially some kind of a linearizing optimization method comes under the umbrella or the bracket called convex optimization. So non-linear, linear, making non-linear linear is a is an art, and you have to see whether you can do that or not. So we'll talk about it later. So right now you know that power flow equations are generally, combine all the three equations, are generally, how many of you think they are linear? How many of you think they are non-linear? Okay, because we already said at least one clear evident non-linear equation sitting right here, right? All the three equations together. This one you can treat it linear or non-linear depending upon how you form it. How do you form model? You know, you call it form model. I'll tell you a little bit about how do you form that model, how do you tweak it, and then how do you move it around. What are the ways that you can? So they are actually non-linear. Okay, they are non-linear algebraic equations. So nonlinear algebraic equations do not have a closed loop form for solution. You know what a closed loop form means? Analytical form, closed loop form, analytical solution. You know what analytical solution means? 3x is equal to 7. What is x? 7 divided by 3. This is called analytical closed loop, meaning you can directly manipulate those equations. 3x square plus 2x plus 3 is equal to 17. What is x? You know, you have a quadratic equation in a derivation, you can solve it. They are called analytical form. Analytical form. Now, linear models are not, can be solved in closed loop form. So, how do you solve it? How do you solve the nonlinear models? Are you following with me, or are you stuck? You have nonlinear models, algebraic models, you cannot solve in closed. How do you solve it? You have to solve using iteration. What do you mean by iteration method? You know what you do? You guess. Yeah, you guess and check. Then you adjust your guess and check. Not trial and error. Yep. Trial and error does not have any method associated with. Iterative methods have guess and check. Are you following? So these are actually three methods to solve the power flow. They are all nonlinear solution methods, and they are using the method of what we call it as guess and check. One classical representation of solving a nonlinear equation is using a method proposed by Newton, and that's called Newton's method. Okay, this Newton's method, what it really does is you find the gradient of a vector or a phasor, and you go in the negative direction of the gradient of that vector to find the solution. So gradient of that vector can be found and can be gone into negative direction if the gradient of the vector is generally linear in nature. If the gradient of the vector is linear in nature, you go against negative slope of that linear function. Negative slope meaning depending upon the slope. If the slope itself is negative, then you go positive in the opposite direction of that slope, and then you will be able to find a solution. That is what the Newton has proved, and that is called the Newton's method. And Raphson, another engineer, connected together with Newton, then developed a method called Newton-Raphson power flow method. Similarly, Gauss-Seidel and all that. So what I'm going to do is I'm going to pick one method, Newton-Raphson, and fast decouple, and probably go through that with you in a very fast form. That's not a part of it, but so if you wanted to run the power flow method, you are going to run the power flow method nonlinear equations. That is basically what we are doing. We are running the power flow method in non. Can also participate, or don't know whether you are part or not part, but after some time you become a part. Education is always Newton methods. If you run it, you will run the methods to solve the nonlinear equation. Now let's look at a nonlinear equation. What are the nonlinear equations that you have? Apparent power. Apparent power can be written in form of two quantity. One is active power and reactive power. So you have two equations, active power and reactive power. Is active power of a I think you already know this, but some of you may be a little bit bored because you might have heard this. Some of you may be teaching those, but I'm just going to reiterate. Active power and reactive power. These are the two things that if active power and reactive power on every bus, you should know. Right? Can you find the active power and reactive power of every bus? For some bus, yes, some bus, no. I make a statement like that. What does that mean? Let's suppose I have a load connector. in this house or in this building, and the load active and reactive power is known to you, connected on that bus. What will be the active power and reactive power on that bus? That load, which is known to you. So do you want to do any math to calculate that power? You already know that. You see, but there is a bus, there is no load connected. I don't know what an active power and reactive power is. Do you need to calculate it? Yes, I need to calculate. So for some bus, you need to have an active power and reactive power known. Some you don't have an active power and reactive power. Okay. What are the other things which you should know to solve the power flow? You can actually solve it looking at it here. So there are two ways you can write the power equations. Everybody know that? You can write the power equations. Current power S is VI conjugate. In fact, three ways. VI conjugate. Can I write apparent power in another equation? V square divided by Z. Is there another equation that you can write the I square times Z? These are three different ways you can write the power. Same power, right? What does that mean? Power is obviously, need to calculate, right? So I can represent the power which is not known, S, which is P and Q. What else I need to know to solve it? Let's assume that I represent in terms of voltage. I need to know the voltage, V square divided by Z, solve it. Voltage, when I mean by that is, I need to have a voltage and angle of the voltage known, right? Because they're two different quantities. So how many variables I need to know? P, Q, V, and angle of the voltage represented as delta. So you have four variables I need to solve. And how many equations I have? Active power equation and reactive power equation. So how many equations you have? How many variables you need to solve? So there is a challenge. In general, if you have two unknowns and two equations, then you can solve that equation. If you have four unknowns and two equations, you cannot solve that equation. So there is another challenge. One challenge is it's non-linear, and we will solve using iterative methods. Assuming Newton has developed something, we'll go with that. Another challenge is these are two equations. So how do you solve that challenge? So people will come up with a trick or a physical system related trick. The trick is that if I know the load connected to a bus, for all the buses where the loads are connected, I assume that P and Q is known. So what do I solve? V and delta. Okay. So I have two equations, two unknowns. What happens for a generator bus? When the generator is connected, I assume that the power from the generator going out is known or controlled. It's actually not known. There is a device in the generator which controls the power going out from the generator. What's the name of that device? A controller in the generator that is controlling the power going out from the generator. What's the name of that controller? Somebody. I have two choices. I'll only pick the wrong one. Right? There's only two controllers in the synchronous generator control. Only two controllers. What are the name of those two controllers? What are the name? Huh? What? Automatic voltage control. Automatic voltage controller is connected to a box in the generator called excitation system. Excitation system, automatic voltage generator. That's one control. What's the next one? Load frequency control is not done at a generator. Load frequency is controlled at the system level. To get to load frequency control, somebody is doing control on the generator. Who is making frequency 60 Hertz or generator runs at synchronous speed? The second controller in a generator is called governor. Governor is the one who governs or controls to make the speed of the generator constant when the speed changes. So will the speed of the synchronous generator changes? Ideally, no, because it's synchronous speed. But when the load is changing, the generator is not able to supply the load. So load is here, generator is here. For some time, the speed wobbles. So because of that wobble in the speed, this box called governor sends that and opens the valve for the generator, pushes more fuel to the generator from the generator to maintain the power from the load equal to the generator. This is spun in 3 seconds. That's the response time of the governor. So the governor is one controller and the excitation system IBR. What does it what? The governor is controlling what? Power, voltage, frequency. Governor is controlling. Governor is not necessarily controlling frequency. Governor is controlling speed and the power coming out from the generator based on the speed. Who is controlling the frequency? All the layer together, load frequency control and everybody together. Layer meaning there are different layers. Above the generator, there is a layer called automatic generation control called AGC. Then there is a layer called load frequency control. This is basically done with AGC and some other things called tie line control and all that. It's like a story, it's not a part of this course, so we're not dealing with that. But the governor is used only at a fundamental unit level to control the speed as well as the power going out from the generator. And the excitation system and IBR is controlling what? Voltage at where? At the terminal of the generator, where the generator. Oh, will this IBR and excitation system control the voltage at my home? Because it's important. I'm just saying that is because so it once controls the voltage and one controls the power. So what is our thinking? I'm thinking that active power and the voltage I know. Why? Because I control. So if I know active power and voltage, I can calculate the reactive power and the angle for the generator. So you may ask, oh, all the buses are generator and the load. Is there a bus without generator and without the load? Yes, there is a bus without generator and without the load. Do I need to calculate something on the generator? No, that's a different one. Do I need to control the power on a bus that is no generator and no load? Do you have a bus with no generator and no load? Yes or no? Yes. Yeah. Why I don't know. So do I need to know some variable? Well, if you have a generator with no generation and no load, such bus we call it pseudo bus, meaning those bus power coming in and power going out. You can write the power balance equation. You don't need to do any math to do that. Now we also have a problem. What is the problem? This is great, but who will take care of the losses on the electric network? How do you know the loss power? If you know the power of the losses, power for the losses rather, I can take the number and add it to this math and I am done, right? Who will take care of the power for the losses? Do you know that? You don't know that, right? So the power for the losses means what? P and Q. There are two losses, right? Actually, so there is a loss term that needs to. So what you do is that we say that one generator will take care of the power for the losses. That generator, we call it a highest generator, and that generator is the one who is delivering all the losses in the world. And you will, for that losses, you will know that P and Q is not known and V and delta is known. That one single generator is called slack generator or a slack bus. Is one generator supply the losses on the entire transmission network? Do you believe that? I also don't believe that. So why did we make that? We make that because that's the only way we can solve it. So it's not realistic. It is just for a method of solution. Now, if it is not realistic, do you believe it? Do you know how it will be correct? It is not realistic, but it is close to real. The reason is highest generator or largest generator will supply most of the losses. So 70-80% of the losses may come from that generator. The rest will be taken by other So these solutions are not exact. If you go and to check it in the real life, it's not going to be exactly true. Is that okay to have a solution given by the power flow which is not exactly true? Yes, it is okay because we are using this for planning purposes or some studies. We are not using it to find out the changes in every dot with respect to time. So there are methods that people are going out from there and solving that problem to what we call it as distributed generator problem and all that. So we solved two things. We solved the nonlinearity thing using Newton's some stories about that, and then we also talked about how to write two equations and two corners. So there's three different ways you do that. You understood what's going on in here. So you have power balance equation written. Oh, so now that same math that we represented before in the slide, you started writing that math in the form of that math you see there is written S. What's the first change you see here? Instead of S, it is written E and Q. Why did we do that? Why did not we stayed with S and then moved to P and Q? You just said, huh?
Represent active and reactive.
Why? Why do we need active and reactive power? We need two equations. Remember, then only we can solve. So we represent the same one as equation into two equations. Okay, we did one more thing. What did we do here? As S was V times I conjugate. Remember that S, right? V times. Is there I here? No. What did we do? We changed the V times I conjugate to V square over Z representation. You see V and Z. 1 over Z is Y, you are representing that, and you call it Y, so generally we represent as a Y bus, if you may recall. V times V divided by Z or Y, and you represented that in here, right? And we did one more thing. What did we do here? We break this into P and Q. We wrote this in what form? Complex number is written in what form? Rectangular form or Cartesian form, where you do one as cos, another as sine. P plus jq is cos plus j sine. This is called Cartesian representation or rectangular representation. Can you represent that in the polar form? Everybody know polar form, rectangular? I cannot go to that level now because we need to move. Polar form is a magnitude and angle, so this is represented in. So three things you will notice in this equation. One is 2 breaking into 2 quantity. Second is writing in the terms of voltage and Y, and the third in the form of Cartesian. Okay? So this is very suitable for power transmission network. Why? Because in the power transmission network, you don't really talk about the flow of current on the like a distribution network. You can keep the voltage and then solve using node voltage analysis or voltage analysis. So it's very good in representing that. Now what you do is that you look at the power balance equation. This power balance equation was there, which is calculated power minus scheduled power, and calculated power minus scheduled power should be equal to 0 along with the losses. And then the change in the power is what you use that as a mismatch. So how do we solve this? You solve the change in the power and look at the change in the power. First time when you start it, the change in the power will be too big. Then you guess, check, guess, check. Go to the change in the power, find the gradient of the change in the power and go in the negative direction and solve it. So we have a conceptual idea about that. So what we will do then is since we don't have a lot of knowledge there, I will go to my backup slides and I will show you. I was not planning to discuss about this, but I'll take 5 minutes, not more than that, because we may not reach there, to solve about the Newton-Raphson. I'll just stick with Newton-Raphson, maybe some derivative of other power flow. So this is basically a Newton-Raphson power flow in a network which has got voltage and current going out, and you represent the current in the form of Y times V, and Y is called the Y that we saw there. V is called the V of the node or the bus. Okay? So if you wanted to do this, you need to know the power flowing through the network using KCL. So you say the total current injected is equal to the current flowing through every branch. How many branch you have? Whatever branch you've connected to. And the total Y is going to be 1 over Z, and you can call that, each Y is going to be 1 over Z, and you can call that. I hope, and this side you are able to follow what I am talking about. I am seeing from faces that some of you are punching out, but I have to move fast, so hopefully you will be able to. If you have, you are completely zoned out, you got to raise your hand so I can help you with that. Are you following? Are you following? Oh, they are okay. So they are not in. So you can leave them. And other people, are they following? Are you following? So, so that is. So what we are doing here is we are writing the form of V and Y, and we are representing the power flow in the form of V and Y. So you see that in here, how you can represent that is by collecting the KCL equation for a 3 or 4 bus system. You can write the KCL equation in the form of I1 and I2. Current going in is equal to current going out. So you can write current going in is equal to V times Y plus V times Y. Is that easy to read? Is a complete pure Kirchhoff's law. And what happens? There is no current flowing in. This is very easy to write. You don't have to current flowing. You can write it 0, and then you write the equation. So what you do is that you collect the currents in the form of Y, V times Y, and this Y, small y making a big Y is called Y bus. Okay, and Y bus is a representation of all the small y's in the system. The KCL equation, you can expand that into the Y bus just by looking at it. How do you look at it? You look at the diagonal elements and you add all the diagonal element y's together connected to that node. All diagonal elements are negative. Y is connected on that. So with that, you can actually get a complete Y bus. And after you get the Y bus, you can write the nonlinear equation that is coming from expansion of the nonlinearity with the change in the deviation, and based on what we call it as a Taylor's expansion. I don't know whether Taylor expansion or Taylor series expansion you might have heard in your undergrad. What is a Taylor series expansion means? It means that any higher order system can be represented in the form of change of that function with respect to the change in the variable. These are not a differential equation. These are okay. Why they are not differential equation? Because there is no df divided by dt. They are not time differential equations, but these are change with respect to the function with the variable. So change with respect to the function with the variable is generally called sensitivity. Okay, change in one function with respect to the variable. So these are sensitivity equations for each of them. So what you do is that you get a higher order derivative. So you kind of ignore this part, and you ignore this part, then you have f of x 0 and then this delta x. So if you do that, ignore the higher order part, you can find the change in the x by looking at the change in the c divided by the sensitivity matrix. Okay. So this is a math behind it. Not a very difficult math. That math tells that this is how you find the change in the x. And if you know the change in the x, you add to original x, you find the new x. And you repeat this. You repeat this process. Okay. So having said that, are you okay with the speed, or please, some of you are good, we have to drag all of them, but that is how you represent with the change in the. So what you do is, you need to, what are the things that you need to know to solve this? To get delta x, what do you need? You need this and this. Okay, count on it. What is this means? Delta c. What does it mean? It means the change in the c with respect to f of x. What is f of x? F of x is a calculated power in our case. What is c? It's a constant power that we want to deliver, which is basically scheduled power. So this c is a number and this is a calculated power. So to do this calculated power, you need to calculate the power first. And then you find with a change in the number, then you get this. And then you also need this. So to calculate the power, you use the power equations and you divide the power equations into two parts. Classically, we call that as Vy cosine equation and Vy sine equation for the active power and reactive power. So you have to solve this equation, get this. Then only you can start the process. How do you solve those equations? Do you know delta? Do you know V? Do you know Y? That's coming from Y bus. Do you know theta? That is coming from Y bus, angle of it. Do you know the deltas and V? I don't know. That's why I wanted to solve, right? But I need to start. How do I start? You start with a number that you think is great. That number for a V is 1. The number for the angle is 0. Okay. That starting point for the power flow is generally called flat start. I don't know whether you have heard of this term. Flat start means starting at flat. Will the final voltage be 1? I don't know. Final voltage be 0, or angle be 0? I don't know. So you start from a flat start. If I do that, I can solve this equation. Okay. So once I solve the equation, I will be able to get this P, and I can this one. Then I will be able to get this C. Then I can find the change as long as I know this. Right. This one right here, I need a change or sensitivity written for the P and Q. This sensitivity matrix for the P and Q, I write it together in one matrix, and that matrix is called Jacobian. Okay. So Jacobian matrix is a first derivative of the function with respect to the state variable. Okay. That function is P and delta, P and V, Q and delta, Q and V. So you write that, then you will get a Jacobian matrix. That Jacobian matrix, you write it. So how many delta you have? Depending upon how many bus I need the delta to calculate. All the buses, do I need to calculate delta? No. All the buses I need to calculate V? No. We told you what to do, right? Which bus what. So you write like that, then you get the Jacobian, and you have to do the derivative. So derivative with respect to, oh, by the way, this derivative is a special derivative, and they are called partial derivative, because you are not finding the changes one variable to the other in full. You are changing the one variable to the other in part, which means you are going to fix one variable as a constant and then find the derivative for the other variable. If you do that, you will get this math, and that math is basically, you should be knowing. Once you know that math, you can solve the using flat start, you can solve the power flow. So for example, for a 3-bus system, we can solve the power flow with the you can as an example. If we are excited and if you want to do this, we can include that in our problem solving session tomorrow. I can give you this example. You can solve this for Newton-Raphson power flow. No strings attached, meaning no grades and no problem, but you can solve it in the problem solving session or some other time. So that is how we solve the Newton-Raphson power flow. Good. Okay. So you can, let me just say one part here. So now you say, wow, that's too much. A lot of derivative I need to calculate and then solve it for entire power grid. A lot of work. So you can say that this P and delta is, we call it very tightly related. P and V is not very tightly related because the active power is not very tightly related to voltage in transmission network. Not true for power distribution network because of some other things called X divided by R ratio or some other quantity, which we will not be able to talk about it now. But in general, say they are not tightly related, so you can actually ignore them. This and this. If you ignore them, then you can solve it only on this. Okay, that is called fast decoupled or decoupled power flow equation. We are not using the coupling of these two. So what happens if I don't know this topic on power flow and transmission system? Some of you, are you all able to follow what I was saying? If you don't know about this topic, don't worry. We will work on this topic part again one more time. But that's something which you can at least think about in baseline. All right. So coming back, what do we have now? We have a knowledge about this, right? Do I need to have a knowledge on a distribution system how we solve the power flow? Yeah, I need to have some knowledge. Otherwise, I cannot solve it. Integrated. Remember, integrated. That's the goal. Okay, so just talk about distribution system power flow. So distribution system power flow, you have a power supplying and power receiving, and they are coming through a distribution line, a switch or a transformer. Did you remember the modeling of transformer, which is tapped transformer, voltage regulator, OLTC? You remember the modeling of lines, right? Distribution lines, impedance. And you also know there are some switches that can happen on the distribution. And do you remember the name laterals? Yes. How many of you remember the name laterals? What is lateral? Did we talk about it? Yes or no? When? This morning we talked about baseline one. So the laterals are right here. So all these things you should be knowing. So now you can say there is a cogenerator. Cogenerator is a DER, shunt capacitor connected, and the load connector. These three can be connected in one node. So you can represent the current, power, and voltage. That's basically your distribution network. So if you wanted to represent the distribution network, there are some challenges. One challenge is this distribution line that you are going to see has to be modeled in each phase. Remember the transmission line when we are modeling resistance, inductor. One. Why? Because all the three lines you are going to say. So one representation is resistance. No resistance, you ignore. Then I have the inductor. That was very simple. Here you need a resistance. Can you ignore? No, resistance are there in the distribution. I cannot ignore. So you see one resistance in another resistance inductor, third resistance in inductor. Voltages or current flowing through each one of them. Are they balanced? No, they are not balanced. And I ignore the current in here in each one of them and then say they are balanced? They are not balanced. If they are not balanced, what will happen to the voltage in each of those lines? Voltage will be changing, right? If the voltage is changing, how do you represent the voltages? You represent the voltage by adding some capacitance effect on those lines to represent the voltage. So having said that, A, B, C and neutral, all these lines, 3-phase 4-wire or 3-phase? Everybody know 3-phase 3-wire, 3-phase 4-wire, 3-phase 4-wire or 3-wire? You will need to have this. So you got to represent them in the form of impedance plus the capacitance on diagonal element and cross diagonal element representation of the series representation of this 3-phase impedance. And you got to represent A, B, C means what? Each phase. So one line, second line, third line. So there will be 2 by 2 by 2 matrix connected on each one of those lines to represent one segment. Like that you represent for all the segments. So lines that are connected in series and admittance will be represented like this. Okay, so that's how you represent distribution system lines. That course is not on undergrad level, so I don't know, here distribution system course are mostly on the grad level, right? Advanced topic, it's not a undergrad level, so I don't think you. How many of you have seen this type of modeling for distribution system lines in your life anytime? No, this is something that is how we model the distribution network. Are you catching what is the difference between a general transmission? No, right? Yeah. So this is how you represent distribution system line models. Okay, so let's catch up with some key difference. What's the first difference? We represent each line. So it will be 3 or 4, depending upon that many elements will be there in your one line configuration, right? Second, you represent the of diagonal elements and diagonal elements depending upon whether there is a series connection or we want to represent the dynamics or not. So that's a full detailed distribution line representation. If you represent the transmission line in a 3-phase form, you represent the same way too. However, you don't have to because you don't have that requirement for the transmission line. Good? Okay. So the next one is voltage regulator. You can represent the voltage regulator in the form as Y, ABC for a regulator, with the R being the inverse of the tap for the regulator. So this is a 3-phase regulator of voltage regulator. Okay. What do you mean by 3-phase regulator? Regulator connected on each phase. Can you have a 3-phase regulator with one single phase multiplied by 3? You know what I'm talking about? One single phase. I have a regulator or a transformer with a single phase. Okay, connected, right? You know, single phase transformer or no? One phase connected on two windings. One winding in one phase, another winding in other side of the same phase. That's called single phase transformer. Okay, and if you represent that 3 of them, they're called 3 single phase transformers with each line. Now you take all the 3 single phase winding and connect in the form of Y and delta. Do you know Y and delta? Everybody know it. You connect in form of Y and delta, you'll get 3-phase transformer. Okay, you can have all the 3 phase windings connected together. That's called 3-phase transformer. So you buy a transformer from the market, you may get all the winding connected, all the 3 connected together. It's called 3-phase transformer. If you have independent transformer connected and you are asked to connect it outside, that's called single-phase transformer. So you can represent single-phase transformer multiplied by 3 on all the 3 phases. If you do that, you will be able to see configurations like this. Each of those phases can be controlled or tapped, right? So that's basically your voltage regulator. And then you can actually have a loads connected in the form of zip configuration for the loads connected on each of those lines in the form of 3-phase, 2-phase or single phase. When you 2-phase, you connected in Y and or in delta. I'll skip this part a little bit. This is how you represent the inverter-based resources or DERs. Okay. So I will talk about this DER integrated part. There is another session, so we'll talk about that during that session. How do you run the power flow? One easy way to run a power flow is called forward, backward, sweep power flow. How many of you heard this word? Forward, backward, sweep power flow. Not that difficult. If you don't hear it, no problem. We will do it now. Forward, backward, sweep power flow means you are going to represent the voltage on the distribution network knowing the current. Okay. So how do you represent the voltage on a distribution network knowing the current? Oh, by the way, the voltage goes down on a distribution network all the way to the end, right? So I'm going to talk about, let's assume you have a 5-node system. You know, 5-node system, and you want to talk about 5 nodes. Each node has an impedance and loads connected in for at the end. Okay. The way to solve this is the trick, what we talk about to solve on a distribution network. Oh, by the way, is this distribution network consist of the problem that we faced on solving power flow in transmission system? Remember the transmission system power flow, when you solve it, what are the challenges we faced? First, they are nonlinear in nature. Second, 2 equations and 4 unknowns, right? So here your goal is to talk about the voltages at each point, right? So what are the unknowns? Just the voltage on each point. So what you can look at to see what will be the voltage here and then calculate the voltage back there. So it's a 5-node system that we are considering. And how do you start? You start by taking the voltage at this point, the forward time, And this voltage, you assume that there is no load connected. If there is no load connected, this voltage will be no load voltage, which will be assuming that as 1 per unit. Start from flat start. If you have a 1 per unit voltage, can you calculate the voltage here? Yes, you have a drop, you calculate the voltage. We have a voltage calculated here. Can you calculate the voltage here? So, on the forward sweep, you compute the voltage at node 5 under no load condition. With no load current, there is no line current, nothing is flowing. So, you run. Then in the backward sweep, commences computing the voltage load current at that node and then this current. So, you know the voltage, you can calculate the current and then you go backwards. Okay. So, to calculate the load current, you use this equation. You know this equation. Okay. S equal to VI conjugate. And then after you compute, you go to the node number 1. And once you look at the source voltage 1, you calculate the specific source voltage and you do this iterative sweep again. Oh, they are not linear in nature, but you don't have a problem of 2 unknowns and 2 equations because you are actually 2 equations and 4 unknowns because you are actually not running the generator side of the power flow. So we'll do maybe an example. Okay, this also will tell you something interesting. See this impedance here? 1, 2, 3, 4, 5, 6, 7, 8, 9. This is the impedance between 2 points. How do you represent an impedance in a Y bus in a transmission system? 1 divided by Z12. 1 divided by 3 plus J5. Here, 0.8 and why you have 9 of the elements? Because you are representing them in the unbalanced form for the entire matrix for the 3 phases. That's the reason you have 9 elements. 3 multiplied by 3. That's why you have 9. You see that? Remember this right here. I'm talking about this. When you look at this equation, you think it's very complex, right? A lot of things here. This is how you represent for one line. Right? How about this next line? Another equation. Okay, another 3 by 3. So you have a 3 by 3 matrix for 3 lines. 1, 2, 3. Why 3 by 3? 1 to 2, 1 to 3, 2 to 3, 2 to 1, 2 to 3, 2 to 2. Right? This is off diagonal and diagonal. So you have 9 such numbers here. Where do you get the number? Well, you can calculate this number. There are methods that you can use to it. So if anybody working on distribution network and doing power flow associated with that, this is how you should be modeling the distribution network. So you see this number, this is given to you on a power system to run that. So Z12 and Z23 are given. So what you do, you initially voltage are set up on this for the V1 right here. And this is standard voltage. You assume they are all the same. And the loads are defined in here, calculating the loads in 2 places. Oh, this load is a 3-phase load or a single-phase load? How do you know? Everything is 3, okay? These are 3. Power distribution network, power flow is 3, not 1, because we have 3. So is this a 3-phase load or a single-phase load? It's a 1 load, single-phase load, connected to only 1 phase. How do you know? Because the other 2 numbers are 0. Which phase the load is connected to? Phase B is connected to. A and C are not. How about this? All the 3 phases, they are loads connected. When you have a 3-phase load and single-phase load, yes, you have your home. When you have it, you have single-phase power. And your home, when you are in a commercial building, or you have 3-phase power. You follow what I'm saying? So this is how you see. Every time it will be 3. Multiplied by 3, not 1 equation. Okay, so you find the S divided by V. So in a standard circuit analysis, you can find the V out, V in minus Z I, and based on that, you can do the backward sweep. So you go back and calculate the load divided by the voltage, calculate the load divided by the voltage, you get the current. From the current, you add the load to, you get the power flowing in the I23, and from the power flowing from I23 and the load connected, you can find I12. Now if the node 1 is the last node that you have, which is a head end, you stop right there. After you stop right there, what will you do? You calculate the voltages. So this voltage is 2400, this voltage is fixed. Then you try to calculate the next voltage, you get the next voltage. Find out the difference between the first voltage, first time we use this voltage, then you iterate, get this voltage. Is a difference 0? No. So there is a difference. That's error thing. So what you do is you take that new voltage, continue to calculate the V3, find the difference. After you find the difference, if it's greater, you repeat to calculate V1, V2, V3, take in each iteration and finalize the voltages on every time. This is called, I just storyboarded quickly. You will have a problem solving session and you can solve it, by hand. So you calculate, look at the error and then finalize error and then you keep doing that. And such way of solving the voltages on a distribution network with the power flowing is called forward, backward, sweep. How many minutes we have now? We're almost done now. So when we come back, we're running a little behind. I wanted to talk a little bit about the integrated power flow. So what we will do is we have to buckle up for tomorrow to start a little bit faster on a fast space. Then only we can get to that. Because our goal for this was to do the integrated. So how do you do it? Maybe can I have 5 minutes maybe, everybody? Yes. Now we found a way to solve the power transmission network through a power flow called Newton-Raphson, right? We found a way to solve the power distribution network through a power flow called forward backward sweep. We will do these two power flow when we come back tomorrow as a tutorial, right? What happens if you have to solve the power grid with the distribution system and the transmission system together? Okay, what do you have to do? You have to run the transmission system model, then run the distribution system model, run what? Power flow, and then connect them together, right? So I'll take 5 minutes to explain to you. It's actually more than 5 minutes, but I'll take 5 minutes to explain to you how this process is done, and then maybe we can do a small example to illustrate the process. Okay, so there are 2 steps, very critical step to do this, to solve the problem. You understand the problem? Transmission system, distribution running together. One challenge in this is that the transmission system is running mostly using the models, we call it positive sequence representation. Distribution system is running in 3-phase representation. So you have to stand where? Sequence or phase. If you want to combine them, you have to run them together, right? So we will find a way to solve them together. There are 2 different approaches. One approach is called decoupled, meaning you run the transmission system power flow, then run the distribution system power flow, and then connect them. The other one is you combine them together, and one run as unified. Okay? So I'll talk about the first method, decoupled. Okay? So there are two different things you need to do in the first method. First method is to represent the distribution. Let me talk about the method first. So this is a method. You run the transmission system power flow, right? How do you run the transmission system power flow? Do you remember how to run the transmission system power flow? Right? What do you use to run the transmission system power flow? What method you use? You just learned. Newton-Raphson power flow. You run the transmission system. Once you run the transmission system power flow, you run with this. Okay, all plus means that, right? See that? After you run the transmission system power flow, what will you get? What's the output of the power flow, by the way? What will you solve if you solve a power flow? Solve for the states. What are the states in a power flow? What will you solve for the work? You solve for voltages and angle of the voltages, right? These are the states in the power flow. So you solve for voltages and angle of power flow, then you calculate the power, then you calculate the losses, then you calculate the power flow. All those things are unwinded if you know the voltage and angle of voltage, right? So after you solve this power flow, what will you get? Voltage and angle of the voltage. That voltage and angle of the voltage you take. Take for what? For the power distribution system. Where will that voltage and angle of the voltage go? That will go as a voltage for the substation for the power distribution system. Remember the voltage V1 we call 2400, 0, 2400, 120. That number, where do you get that number? This is the number. So you take that number and go to the distribution system power flow, run the distribution system power flow. Output of the distribution system power flow will be power, active and reactive power from the substation. Take that active and reactive power from the substation, put this as the load in the transmission network. This is the load that is connected to the transmission. Then you run the transmission system. Are you following this? This is how you run, and you stop when? You stop when this voltage that you, this power that you send it out, and then the voltage that you calculated between two iterations are small, there you stop. This is called decoupled power co-simulation, or what you call it, integrated transmission distortion. Good? So you can solve this. One thing which is important to do that is you should know this power. How many distribution systems are connected at this point? You don't have an idea. Only know is a power on that spot load, right? If I have a distribution system connected at 5 megawatt, on a transmission end, it may be 25 megawatt, 30 megawatt, because there will be multiple distribution system connected, right? So what do? You got to come up with a method to aggregate the distribution system power to the transmission system power. So the transmission system is representing 14.9 and 5 J. Distribution system is 3.6 and 1.4. You have to bring this distribution system to 14.9 and 5. How do you do that? You aggregate them, multiple distribution system. You have 6-7 ways to do that. One way is to take the power distribution system network full. Then you multiply it by a constant, saying that that's how the power changes on distribution, how many distribution network. Then match with the total load on the transmission network. So we'll see. If we get tomorrow sometime on the tutorial time, I don't think we'll have time for 3 Newton-Raphson backward, forward, and this. Maybe we'll give one small problem and then.
Yeah.
So let's assume transmission system load is 10 megawatt and 5 Q. Okay. So if the distribution system representation is only 3 instead of 10, there are 7 ways to do it. But in nutshell,
my question is, it will come exactly to the same value. Means
then you don't need to worry. Oh, you need to have exactly the same value? Yes, you must have exactly the same value because the transmission system power flow is using that load. on that. If they won't come exactly the same values, you will get a transmission system power flow for another value, which is also okay. But so that's a very good question. So you have a transmission network and you are modeling the transmission network for power flow considering some spot load, right? If that spot load is different, then you are solving the power flow for another condition, not the same condition. Now, normally people don't solve the power flow with different spot load condition. You take the entire spot load and you multiply with a scalable number like 3 times, 2 times, because the load and each point in a network is not changing. It is only changing together like a load variation. So spot load into a different number, if you change, it's a different operating condition. Now let's assume that in the iterative loop, you keep changing this. Then it's chasing the goose. You will not be able to get the same operating condition all the time. So you cannot do that in the integrated loop, considering that that spot load is different all the time. So that's why we need to reach at that same load condition with the given distribution network. But at the same time, you cannot run 15 distribution network along and representing the transmission network. That's too much. Right, complexity. So what you do is you run one distribution network and then say that it's a duplicate copy of that to get that number. Are you following what I'm saying? So inside the loop, it's not allowed to change. You can change it at the beginning and keep that condition all the time. Other questions? Okay, so I think tomorrow we will start talking about the optimal power flow. We will be keeping one time to run the power flow. Maybe same example I will let you run, so you'll get some idea how it's been done, and maybe an integrated example for a 3-bus, 5-bus connected to 3-bus, something like that. So hopefully you will get an idea about post simulation. And tomorrow when we'll start about optimal power flow, and we'll go into a different world a little bit on optimal power flow, and we talk about how you consider cost into the mix and how it's connected with power flow and the differences. So that's basically for tomorrow's topic. In between, if you have any questions or if you have anything that you are not able to understand, or if you have any suggestions to add that you are working on a topic or a study that you want me to include and talk a little bit about that, bring it over. There is no guarantee that I will include everything inside the session time because of the time we are talking, but I can give you extra ideas or talk offline. Good. Okay. This is for you, by the way. So take the most advantage of whatever you want to get out of this. So I'll be able to give you whatever you want. Not all the questions can be answered with my capacity, but I will try as much as I can. All right.
Thank you, sir. Thank you for your systematic approach. You have explained step by step how to go for the power flow analysis for transmission as well as distribution systems. So this is the basically building blocks for doing all optimization kind of thing that will be discussed in tomorrow's talk. So thank you, sir, for this nice discussion in this session. Now this session is over. All the participants are requested to again rejoin the session tomorrow sharp at 9:30 a.m. So again we will meet tomorrow. Thank you all for today. One more thing for the participants, you just revise the things, whatever sir has discussed today, and come with your, if possible, come with your laptops if you are having, because there will be hands-on session tomorrow. So that's all. Thank you.